Okay, welcome back to the next webinar in the Certification Training for Nutrient Management Planners series. Today we're going to be talking about soil chemistry in a fertility primer. If you're participating in this live webinar session, well actually there's no one participating in the live webinar session today. Let's go say you can relay text to us simply by typing in the box below. Otherwise, if you're participating in the recorded session, what I'd like to do is share with you a little bit of information about that will make this easier for you. And if you just hold a second, I'm going to copy paste right here into your text box so you have a web link. Essentially what I want you to be able to do is go in and download the slide set so you have it available to you for note-taking purposes. Also, if you're participating in the online recorded session, you don't have the feedback capability of texting back and forth with Dr. Osmond and I, but we do want you to be able to get to us if you have any questions. So I've given you our 2 email addresses down here in the text box so that you can basically, if you have questions, just email us at any point in time. We'll address those as we go through the rest of the nutrient management planning sessions over the next few weeks. So we start thinking about the chemistry of soil. You know, one of the things, or some of the things we're going to talk about today are the concept of ion exchange, soil acidity and controlling pH, basic fertility principles, where we get into you know, most limiting nutrients concepts, macronutrients, micronutrients, those type of things. We'll spend quite a bit of time on the nitrogen cycle, some time on the phosphorus cycle, and then we'll get into other nutrients, and then wrap up the discussion talking about soil sampling and those type of things. So let's kind of begin. When we start thinking about soil cations and anions, what I want you to recognize is not all nutrients, not all elements in the soil are in a well, very few of them are in a form where you have a negative or zero charge. And so we have these things we call cations and these things we call anions. And cations are essentially ions that have a positive charge associated with them, such as what you can see here: hydrogen, potassium, magnesium, and calcium. Now, magnesium and calcium both have a 2 positive charge, whereas hydrogen and potassium have a 1 positive charge. Anions, things such as chloride, nitrate, sulfate, and phosphate, all have negative charges as indicated here. Chloride with a 1-, nitrate with a 1-. There's actually a typo here. That should be NO with a subscript 3 and then a superscript minus. Sulfate 2-, and phosphate 3-. So cations and anions, and how these guys are going to behave in the soil are a function of the soil chemistry properties themselves. And what I'd like for you to think about is something as simple as a magnet. Okay, so in the case of here, you know, you have the negative end of a magnet as indicated by these negative charges, and out here you have the positives. And what happens when you have 2 magnets and you get 2 negatives together? So a negative end of the soil and the negative end from an anion. Do those 2 magnets attract each other, or do they actually repel each other? In fact, they repel each other, right? The flip side of that is the negative end of the magnet and the positive end of another magnet, and they attract. As you can see over here, where these hydrogens have been attached or have bound up to this thing we're going to call the cation exchange complex, where the positive and the negative are attracted to each other. We'll get into this a little bit more about which nutrients are held tighter in a second, but for the most part, what I want you to grasp is that positively charged things are held in our soils in North Carolina, and negatively charged things are not held in our soils. So let's back up for a minute and think about this. Positively charged things. So hydrogen, potassium, magnesium, and calcium. All those guys get bound up to that negatively charged cation exchange complex, and so they tend to stick around in our North Carolina soils. On the other hand, things like nitrate do not. They're anionic forms and they tend to leach out of the bottom of the soil. Same with chloride and sulfate. Now, phosphate is a little bit different. It's a negatively charged anion, but it does not tend to leach in the soil, and this has less to do with cation exchange, negative versus negative kind of repulsion forces, but has more to do with the fact that phosphate has a tendency to bind with something such as aluminum or something such as iron, and we will talk about those two more when we get to the phosphorus cycle, how those two in North Carolina really control phosphorus availability, if you will. So when we think about something called cation exchange capacity, essentially what we're talking about is how many negative charges do we have on that soil, and thus how many positively charged things can it attach or hold. So for example, here we can, let me see if I can get a different color pen. So negatively charged soils, so we have more negatives. There we go. That should be sufficient. So what you can see is that the soil on the left has actually more negatively charged sites there than there. So this one over here has a higher cation exchange capacity than this one over here on the right. Okay, and the importance for that is because this has a lot to do with the cation exchange capacity has a lot to do with the fertility of the system. It has a lot to do with buffering within the system. What do I mean by buffering? By buffering, what I mean is the soil's ability to resist change. So when we think about cations that are held on those negatively charged sites, the more negatively charged sites we have, the more cations that we can hold. And so those things can be, released over time back out to the plants that need the nutrients. It could be a liming issue, the ability to resist changing of pH. So we will get into those things later when we get into soil pH. So I want to give you some examples here. We think about cation exchange capacity. What we do is we put it in terms of something called milliequivalents per 100 grams of soil. Milliequivalent. So we're basically talking about charges here. How many positives charge per 100 grams of soil can we absorb? Or how many negatively charged sites are there per 100 grams of soil? And we can this cation exchange capacity thing differs with types of clay, amounts of clay, and the amount of organic matter. For example, clay cation exchange capacities can range anywhere from 10 milliequivalents per 100 grams to up around 100 milliequivalents per 100 grams. Organic matter, on the other hand, they're looking at somewhere around this, 200 milliequivalents per 100 grams. So if we have a system that's got some clay with 10 milliequivalents charge, and then only a little bit of this organic matter, what you can see is that the cation exchange capacity of this organic matter is what, 20 times as much as some of the clays, and so a little bit of organic matter can have a big impact on this cation exchange capacity in the soil, if you will. So we can think about high cation exchange capacity soils as things that are in this 15 to 40 milliequivalent per 100 grams of soil range versus these things that are low, 1 to 10. When we think about things that are low, or excuse me, high, what we're thinking about are things with high clay or organic matter content. These are soils that have got, they tend to hold a lot of cations. They tend to hold on to hydrogen, which is a cation, and so they're pretty resistant to changes. They've got what we call a great buffering capacity to them. So you get in these low cation exchange capacity soils, and these are things like really sandy soils, high sand content kind of soils. And these are soils that don't hold on to cations very well. They don't tend to buffer pH changes very well. So the point of where I'm trying to head with this is that when we start thinking about fertility, this concept of cation exchange capacity whether it's high or low, is going to have a lot to do with how do we make our determinations on we're going to fertilize frequently or not. Are we going to have to, go out there and sample for Lyme every 2 years, or can we get by with every 3 years? It has a lot to do with cation exchange capacity. So let me explain to you, what do we talk about when it comes to cation exchange capacity? Well, what you're looking at in this picture over here on the left is these are what we call clay mineral layers, if you will. And if you've ever had any kind of soil classification or introductory soil, what you'll see is in soils, you have these things that are 2-to-1 or 1-to-1 type of clays, where you have a layer of aluminums, a layer of oxygens, a layer of aluminums, a layer of silicons, and you have these in various orders. The result of these type of minerals, one of the things that happens with these type of minerals is that they get these negative type of charges that circle around the outside of these layers. So you have these negative charges. And what do we have floating out here? Oops, that's a negative one right there, actually. What do we have floating out here? We have hydrogen, calciums, potassiums, magnesiums, etc. And those things tend to get attracted towards those negative charges that are on that clay. All right. Now, organic matter is a little bit different. Actually, it's a lot different. We don't have these mineral structures like we have in the clay mineral world over here. What we have in this case is we have organic compounds. Now, if you were to, this is what the theoretical model of organic matter looks like. So basically, if you were to digest organic matter, figure out how much carbon is in there, how much hydrogen, how much oxygen, nitrogen, etc., and throw that into a computer and say, now piece all these components together to where you fit together logically. This is what organic matter would look like. And the thing I want you to notice is around organic matter, there are a lot of these OH groups. There's one, there's one, there's one, there, 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 there. I could sit there and do this 100 more times this morning. And basically what I'm trying to point out is these OH groups. Now, why are the OH groups important? Well, organic matter, when you start changing the pH, things can happen, such as that hydrogen right there can be lost. That one can be lost. That one can be lost. That one can be lost. So as you lose these hydrogens, you create right there where that hydrogen used to be. So let's go in here. Let's get rid of that hydrogen. So we X'd out that hydrogen. What do we now have? We now have a negative site associated with that oxygen. So let's get rid of this hydrogen. What do we now have? We now have a negative site. Okay. So remember, over here on the clay charges, we had these negatives like that. So here sits our negative charge. Over here on the soil, with the organic matter, there sits our negative charge. All right. What does that mean to us? Well, in order to change cation exchange capacity on organic matter, or in order to create this cation exchange capacity on organic matter, what did we have to do? Well, we had to get rid of some hydrogens, right? That means that this organic matter kind of cation exchange capacity is very pH dependent. As you change pH, these cation exchange capacities change. Over on the mineral soil, well, these negative charges are kind of built into the structure themselves of the clay particle. Now, I indicated earlier that we would talk a little bit about, strength of absorption. And there's a couple of things I want you to think about. One is the number of charges. Let me see if I can get a better looking pen. All right, one is the number of charges. So aluminum with 3, calcium with 2, magnesium with 2, and then potassium. All right. So obviously the things that are 3+ charge are held tighter than the things that are 1+ charge. As you continue down this path, though, what you see is there are some cases where some 1+ charges are held less tight than other 1+ charges, and this kind of gets to be challenging to understand. What I want you to think about is this. So I'm going to draw you an example of an atom. All right, so this is going to be sodium. The plus charge is actually in the very center of that atom, all right, of that element. So over here, let's have our clay, right? So the ability for, the bonding strength of this sodium is affected by the fact that you've got this relatively large diameter type of atom here, and so that plus cannot get, that plus cannot get very close to these negative charges. All right, so let me see if I can erase sodium for a minute. Sodium's gone. Oops. Let's get rid of some of these other things. All right. So let's draw, let me go back and draw sodium now. So here's sodium, big atom, plus in the center, and here is another atom, potassium. Now, which one of these is going to be able to get that positive, that guy right there, closest to this clay? Well, potassium can get in like that. It's held pretty tight. Sodium is like that. So just like with two magnets, the further away you get the positive end of one magnet from the negative end of the other magnet, the less attraction they have. So these two guys attracted fairly tightly. These two guys, not so. All right. So those are things that are kind of affecting the strength of absorption. The point being that things like aluminum are held tighter than calcium, which are held tighter than hydrogen. Okay. But does that mean that we can't replace what's on the cation exchange complex with something else? So let me draw my cation exchange complex again, all right? So here is an example of, here's some hydrogen on there, here's some aluminum. I guess I need a 3 charge, and a hydrogen there. So this hydrogen, oops, let me get my other pointer. So that hydrogen is associated with that negative charge. That hydrogen is associated with that negative charge. And that aluminum, remember, aluminum, 3+, right? So that aluminum is associated, with that charge, and that charge. So is there any way to get rid of this aluminum? And the answer is yes. Well, if you come out here in the solution somewhere and you just put in a whole bunch of calciums or magnesiums, so you increase the concentration of these guys quite a bit, they can in fact displace this aluminum, which is held tighter in theory than the calcium and magnesium. Okay, so it's a combination of things going on here when we start talking about manipulating the cation exchange capacity. One is, what elements are we talking about there? Calcium, hydrogen, magnesium, aluminum, or sodium. And what is the concentration of those elements? So this really has us right into this discussion about soil acidity, because soil acidity has a lot to do with calcium, magnesium, aluminum, and hydrogen. So first of all, what in the heck is soil acidity? Well, it's most certainly one of the most important factors when it comes to addressing the chemistry of the soil, because as pH changes, the availability of certain nutrients change. Some get more toxic, some get less toxic. Some get, you have greater chance of deficiencies, or in fact, or those toxicities themselves. I'm sorry. All right, so think about acid soils. By definition, those are the ones that are below a pH of 7. So on a scale, you have 14, and you have 0, and right here dead center, there's 7. 7 is what we call a neutral condition. Down here is acid conditions, and up here is basic conditions. So we have acid conditions below a pH of 7, basic conditions above pH of 7. And typically in North Carolina, you know, where we're at is we're somewhere in this range right here, this 4 to 6 kind of range for our soils. And, you know, a lot of this in the mineral soils has to do with aluminum. The aluminum has the ability to drive the pH way, way down. So let me give you some examples of pH just to kind of get you thinking about pH. So pure water right here, pure water is somewhere in that, or it should be 7. Pure water by definition should be a neutral pH, so 7. So rainwater, somewhere around 5.5. Why is that? Well, we get this stuff called CO2. All right, every time you exhale, you expel CO2 from your system. Well, CO2 dissolves in water and makes this stuff called carbonic acid. It's what makes sodas fizzy. All right, and that has a pH somewhere around 5.5. You can get down here, battery acid, you know, that's pretty darn low pH. Vinegar, 3. On the other end of the scale, we can have things like baking soda, antacid tablets, those type of things. All right. So pH, and keep in mind, in the soils world in North Carolina, we are somewhere in this range in most cases, in that 4 to 6 type of range. Well, I indicated, you know, that pH is important, is probably the most important chemical property, and the reason why is because the impact that it has on other nutrients. And so I'd like for you to focus on is here, we're in this pH 4 to pH 6 range in our soils in North Carolina. And we have a variety of different nutrients. We've got, let's see, here's phosphorus, here's calcium, magnesium, copper, zinc, etc. Let's just focus on those for now. No, we'll focus on iron and aluminum as well. All right, so we have these different nutrients, and what I want you to think about is the concentration of any one of these nutrients is described by the thickness of the line. So at pH 8, for example, in calcium and magnesium, concentration is much higher in the soil than it is down here at pH 4.5, 4.75, somewhere around there. And we can tell that by the thickness of this line here. So pH, why is it important? Well, just take a look. I mean, you know, copper and zinc can have much higher concentrations in this 4 to 6 range than it has up here in this pH 8 range. That's important because copper and zinc can be toxic to plants. So what we have here are examples of things that we can do with pH to adjust the toxicity or to minimize the toxicity of copper and zinc to plants. Phosphorus, same kind of thing. You know, when we manage our soils for phosphorus, we're shooting for a pH range somewhere around 6, and the reason being is because that gives us the highest availability of phosphorus. What happens if we get down to a pH around 4? When we get down that pH, we start getting a much lower availability of this phosphorus. Now, I mentioned earlier PO43-. Remember that guy? PO43-. And I said that iron and aluminum are the ones that are really kind of controlling the concentration of phosphate in our systems in North Carolina. So look down here at our pH 4 range when it comes to iron and aluminum. And what do you see? Those are kind of our highest concentrations of iron and aluminum. So we have a lot of this iron, a lot of this aluminum that can bind up. Both these guys, 3+, right? So they can bind up with this phosphate and precipitate it out in many, many cases. We get up in higher pH ranges, 8, 9, somewhere up in this range, and what we start seeing is that calcium and magnesium, particularly calcium, dominates the system. So phosphorus, back to our PO43- guy, right? Phosphorus in high pH systems is controlled by the calcium in this concentration range. Well, I've made a number of comments. It probably seems like I'm spending a lot of time on aluminum, particularly when we're back here talking about the cation exchange capacity, and there's a reason for that. It's because aluminum can be extremely toxic to plants. And so what we're looking at in this case is, here we have barley roots, all right, at a variety of pH ranges, 4.4 to 7.2. So a condition that would not be, much different than what you might find in North Carolina, 4.4, versus a neutral condition at 7.2. And what I want you to focus on is this down here, these things. What are these things called? Those guys are roots, right? So look at the roots at 7.2 versus the roots at 4.4. Which one has a more healthy root system? And it's obvious that the 7.2 does. That's important to us from a nutrient management perspective. That's important to us from a plant perspective primarily. Because which one of these plants, 7.2 or 4.4, which one of these plants is going to have enough of a root system to get it through the drought conditions in the summer in North Carolina? It's certainly not going to be the 4.4 one, right? So the 7.2 one's going to have a lot more extensive root system that can go out there and harvest the water from various places in the soil and kind of, help it make it through the hot conditions. Well, I guess you're not going to have much barley in the summer in North Carolina, but the point being, the larger root system, the more efficient at which the plant can utilize the water that's available to it. Now, when we get further into this presentation, you're going to hear Dr. Osmond talk about something called nitrogen use efficiency. Nitrogen use efficiency has a lot to do with roots. Now, if you put a bunch of fertilizer out here in the soil, let me change color pens. So you put a bunch of fertilizer out here in the soil, right? All these little points, fertilizer pellets, and you have a very, very small, tiny little root system, the chances of that plant utilizing those nutrients are pretty slim. Versus you have this nice, healthy root system which can, capture those nutrients, get them into the plant, and improve that use efficiency. So essentially, one of the things that we're talking about with regards to pH in North Carolina is controlling aluminum. In a nutshell, as the pH goes down, aluminum toxicity goes up. As the pH goes up, aluminum toxicity goes down. So if we can manage our soils somewhere in this range to where we can minimize the concentration, or look, even there, can minimize the concentration of aluminum, we can do a lot to ensure that we have maximum size type of root systems. Now, how does this relate to North Carolina? In North Carolina, our lime recommendations are based on three things really. You have, the measured pH. So what is the pH in the soil on the day that the soil was sampled and analyzed? We have the desired soil pH for the target crop. What does that mean? Well, if you know anything about plants, azaleas have a different pH at which they prefer to live than alfalfa. Azaleas can handle the acidic conditions. Alfalfa can't handle the acidic conditions. All right, so we have a pH that changes depending on which crop we're growing. And we also have this issue of organic matter. pH changes, lime requirement changes as organic matter changes. You might be asking yourself, well, why is that? It has everything in the world to do with, oh man, he's back on aluminum again, right? Back to aluminum. These mineral soils, these bright red, high iron, high aluminum type of soils, have high aluminum concentrations. So we've got a lot of aluminum, a lot of this stuff that we have to deal with in order to make this not happen and make this healthy root system happen. On the other hand, the organic soils, you know, this is organic matter out here. This is not mineral material, so there's not a lot of aluminum associated with this material over here. That aluminum is in a mineral form. It's over here. All right. So the point being is, as we go from these mineral soils to these organic soils, we go from having a lot of aluminum to having not much aluminum. Somewhere in between, right here, lies this thing we're going to call a mineral organic. It's a mineral soil with the heavy influence of organic, but it's not a true organic soil, all right? So our crop-specific target pH, and so what you'll see is that we had three pieces of our puzzle, right? We had what was our measured pH, what is our targeted crop, and then what is our organic matter. And the reason, and what this table outlines here is, here's our targeted crop, and here are our different organic matter statuses, if you will. Our mineral soil versus our mineral organic versus our organic. And so you see things like corn has a target pH of 6 in a mineral soil and a target pH of 5 in an organic soil. You know, soybeans 6 versus 5. Cotton 6.2 versus 5. Then you get to something like alfalfa. It's 5 versus 5. All right. So you can see that there's a change as we go down in this direction. In many cases, there is a change in the target pH depending on the crop. And as we go across this direction, there is a change as we go from a mineral soil to a mineral organic to an organic soil. So we have a crop by soil class kind of a issue setting itself up here. So let's work through an example, and this is the North Carolina lime recommendation model here. It's the way this thing works is your lime recommendation in tons per acre is a function of your target pH minus your current pH. Oops, boy, that was a bad looking line. Alright, so let's go back. Your target pH minus your current pH divided by 6.6 minus your current pH times this thing called AC. What the heck is this? Alright, first of all, target pH. That's your pH coming from this table right here. You know, what crop are we going to grow? We're going to grow, hey, let's do some alfalfa. And we are on a mineral soil. So there is our target pH right there, 6.5. So this value would become 6.5. The current pH is what was measured in the lab over at the NCDA soil testing lab. So I don't know, this is going to be 5.2. I can't actually remember what the number is on the next slide. Well, let's just go to the next slide. So here we go. So our target pH, our crop is going to be alfalfa, so there's our 6.5. Our measured pH is just 5.8 right there. Our acidity is this value, and so doing all the math, and that comes out and tells us that, you know, based on the target crop, the measured pH, and our acidity value, we have a lime requirement of 1.05 tons per acre. So what happens if you take this and say, okay, we're not going to grow alfalfa, we're going to grow lime. I'm going to grow corn. So our value here changes to 6. And you rework all this and you come up with, I don't know what the number is, but you come up with a different lime requirement right there for the amount of lime needed. Another way you can think about this is you're going to grow the same crop, but you're in a different field and the pH changes. So that number is 5.3. Where else do we see measured pH in this equation? Oh, right there. 5.3. All right. And so that would give us a different lime requirement over here. One number in this equation that is never going to change. And let me go back and use this slide. Let me highlight the numbers that will change. That will change depending on which crop you're growing and which soil class you're in. That will change depending on what the pH is in the field. This will change depending on, it's a function of cation exchange capacity. You know, how much aluminum and hydrogen are bound up on that cation exchange capacity. This number will change, right? Because it's the same as that current pH and above. The number that will not change is this. This guy right here will never change, and it's because that is a constant in this equation. So why is this important to you? Well, if you're writing a nutrient management plan and you have to address Lyme type of issues, and you get a soil sample report back that says you're going to grow, you know, alfalfa, and you decide that you're not going to grow alfalfa, well, you now have the soil test values, right? You have your measured pH, you have your acidity. So you have that one, you have that one, you have that one. This guy's a constant. So the question is, if you're not going to grow alfalfa, you're going to grow corn. You know, what is it you're going to grow? Well, first of all, let's black out the answer, because that's not right. So we have to figure out or plug in what are we going to put right there. And so we're going to put in 6.0 and recalculate. And we now have, so you have the tools in your arsenal, if you will, to be able to change the Lyme recommendation based on the crop you're actually going to grow, not the crop that you sampled the soil for. Now, another part of all this liming discussion is the thing we call, or something we call, liming quality. And it has to do with a couple of different things. We're going to really just focus on size, but it has another function is purity. So the more pure a lime material is, you know, the more effective it is. But we're going to talk about size for a minute, because it really does matter when you start thinking about liming. I go back and I ask you a question I asked a couple of webinars earlier when we were talking about soil. Well, I guess you guys haven't heard this one. I'm getting my seminars mixed up. So let me ask you this. Which dissolves faster? A teaspoonful of sugar or 2 cubes of sugar? If you think about it for a minute, you put the teaspoonful of sugar in some iced tea and swirl it, and put the cubes of sugar in iced tea and swirl it. The teaspoonful of sugar is going to dissolve faster. Why is that? Well, it has to do with the fact that the dissolving process occurs at the surface of particles, right? Now, that's a big particle up here that I've just kind of drawn around. And it looks like it has a lot of surface, and it does have a lot of surface. These little tiny particles, though, down in this area, when you figure out the surface area for all the particles, so here you've got maybe, I don't know, 200 particles. Here you have, oh, I don't know, 2 billion particles. So you have a lot more particles, each with small surface area, but the cumulative effect is a tremendous amount of surface area. So the small particles react faster. Small particles dissolve faster. The teaspoonful of sugar will dissolve a lot faster than the cubes of sugar. So why is that important from the world of liming? Well, it has to do with how fast can you change the pH in a particular field. All right, so the greater the surface area, meaning the smaller the particle size, the faster it will react. The smaller the surface area, meaning the larger the particle size, the slower it will react. And so let me introduce you to this concept of mesh. Actually, probably better to do it on this slide. Mesh. Mesh is a size classification where basically we're talking about, let's say, something that is 8 mesh. All right, there is 1, 2, 3, 4, 5, 6, 7, 8. 8 wires in 1 inch in this direction, right? And then in this direction, there's going to be 1, 2, 3, 4, 5, 6, 7, 8, or whatever. So there's going to be 8 wires in that direction as well. So it's an 8 mesh type of screen. Versus something that's 60 mesh, where there's 60 wires in an inch. So 8 mesh, much bigger squares in here than down here. All right, so much smaller particles when you get to a higher number. All right, so much smaller particles here versus here. What do we see happening? So we go out and we apply lime, and so time 0, that would be today. So we go out and apply lime, and it's all 8 to 20 mesh. So it starts this very, very, very slow dissolving process, by which over 36 months the pH has changed very little, if any at all. Alright? What you see though is over those 36 months the pH has not gone down. So this 8 to 20 mesh, although it's not causing the pH to go up, it's not making the soil less acidic, it is at least letting the soil hold its own pH and, in fact, not get worse, if you will, more acidic. So let's look at something like 40 to 60 mesh, where you add 40 to 60 mesh, it dissolves relatively quickly, it comes up, and then over time, as that material is all dissolved, the pH starts going back down. pH 100 kind of does the same thing, but at a much quicker rate. All right. So what you're seeing here is that smaller particles, in fact, dissolve quicker and react faster to change the pH. But larger particles, these guys down here, tend to hold the pH for much longer. What else do we know about size? Here's a question. Which is easier to throw? A bucket full of sand or a bucket full of flour? You can take sand particles, stick your hand down in there, grab some and throw them, and those sand particles are going to, throw. It's not going to be like a bucket of flour when you stick your hand down there and throw it. It's just going to be a big cloud hovering around your head. All right. So although these guys down here react faster, these guys up here are easier to distribute. So is there something we can do that will give us this fast reaction time of these guys and the fast or the nice application properties of these guys? And the answer to that is yes. It's something we call pelletized lime. You see this when you go to Home Depot or Lowe's and buy a bag of lime, this is what you're buying. And essentially what it is that you take larger particles and smaller particles and kind of glue them together, tumble it around, get this nice round spherical particle, so that when you're fertilizing or liming, you get the benefits of the throwing capacity of the large stuff, and you get the benefits of the quick lime fix of the small stuff, and at the same time, so you get the quick fix of that, you get the throwing of that, and at the same time you're also getting the longevity of these larger particles. So you get a quick fix from the small stuff up here, and you get a longevity of the big particles down here. So liming material quality. So let's step away from chemistry for a minute now that you understand a little bit about pH, liming, cation exchange capacity, and those things, and let's start thinking about fertility. We're talking about the management of fertilizers, trying to provide the plant the nutrients that it needs to complete its life cycle. We have this thing we call the Liebig's laws of minimums, and I guess the easiest way to explain the Liebig's laws of minimums is that I can't survive on a diet of donuts alone. I've tried. It just doesn't work. I have to have some protein. I have to have, in my case, some coffee, the occasional McDonald's hamburger kind of thing, right? In the world of plants, the same is true. A plant cannot survive on a diet of phosphorus alone. It needs some nitrogen, some potassium, some water, some air, some sunlight, those type of things. The rate at which a plant can grow, the size at which the plant can grow, is limited to the most limiting nutrient out there, or most limiting growth factor out there. So I can provide all the nitrogen in the world. I can give the plant all the potassium in the world, plenty of water, plenty of light, but starve it of phosphorus. All right? And the plant is only going to grow as to the size at which that phosphorus limiting factor will allow it. All right, and you can kind of think of it like this oak bucket. So we're filling it up with water, and the water keeps spilling out right here. All right, in this phosphorus board. So let's get out our hammer and our nails. Let's pull this board out. Let's replace it with this phosphorus board over here. And so we continue filling the bucket, and what we see is no longer is the phosphorus the limiting factor, but now this nitrogen is the limiting factor. All right. So we get out our hammer and our nails, we pull this board out, we fix the problem, we get our nitrogen board up to here somewhere. What's now our most limiting factor? Well, it's going to be something else, perhaps one of the micronutrients, all right? So what we're trying to do with regards to soil fertility is manage all of these different little pieces of the oak bucket to try and maximize our growth for the plant. So Liebig's laws of minimums. Now the question becomes, how much is required? Now, you know, it's really a function of what plants are you growing in one case, or in a lot of cases a function of what plants you're growing. So when we think about how much is required, what I want you to think about is how much plant nutrients do you have to apply from fertilizer perspective. And you see differences in the nutrients. So nitrogen, you need a lot of nutrients. Copper, you don't need a lot. Nitrogen, you need anywhere from 0 to 600 pounds per acre. You know, this would be an incredible crop right here using 600 pounds per acre. What crops only use 0 pounds of nitrogen per acre for fertilizers? So take a second and think. Can you think of any crop that you need to apply no nitrogen to? Okay, time's up. The answer would be soybeans. You know, things that are legume crops, alfalfa. There's certain tree species that have the ability to fix their own nitrogen. Well, they live in what we call a symbiotic relationship with microorganisms. They have these microorganisms that infect their roots. They operate under one of the deals where the plant says, okay, I will give you some of my sugars so you can grow. In exchange, you will take nitrogen from the air and convert it to a nitrogen form that I can use. And so they live symbiotically. They depend on each other. All right. So nutrient requirements, pounds, etc. A couple things I want you to think about here is look at the differences in the scales. So we're talking about up to 600 for nitrogen, up to 120 for phosphorus. You know, sulfur even lower, magnesium even lower. These guys are much less. And you can start thinking about nutrients that are needed in large amounts and nutrients that are needed in small amounts. Nutrients that are needed in macro amounts, nutrients that are needed in micro amounts. All right. So listed on this chart right here are all the different nutrients that are needed in order for a plant to complete its life cycle. You have things that are in the structure of the plant itself. That would be the plant walls, cells, etc. So carbon, hydrogen, oxygen. Those are certainly required. You have things like nitrogen, phosphorus, potassium, which are macronutrients. You have secondary macronutrients, calcium, magnesium, and sulfur. And then over here on the micros, you have iron, manganese, boron, zinc, copper, chlorine, cobalt, molybdenum, and nickel. All right, many of these guys over here you've probably never even heard of. But they are required for that plant in order to complete its life cycle. And let me explain to you what I mean by life cycle. A plant life cycle is a seed germinates. That seed grows, it reaches sexual maturity, it flowers, that flower's pollinated. That pollinated flower produces some sort of fruit which has a seed inside of it which is fertile, which then is deposited and can germinate itself. So that is a complete life cycle. Now, you can go out there and give a plant 600 pounds of nitrogen, give a plant 120 pounds of phosphorus, and 500 pounds of potassium. You're well on your way to spending some money on fertilizer, right? Okay. But lo and behold, that soil is low in something as bizarre as cobalt. You're missing some cobalt. How much of those, or how well will that plant grow? Well, it's missing one of the key pieces, all right? It's like going back to this oak bucket and completely erasing this board right here. So cutting it out down here somewhere. How much water will that oak bucket hold now? Not a lot, all right? So this plant's not going to complete its life cycle because something as trivial as this thing we call cobalt. So I guess where I'm heading with this is, we'll get into the concept of soil testing later. And what we're really after with regards to soil testing is trying to find, are any of these guys, or any of these guys, or any of these guys, at concentrations low enough in the soil to where it's going to limit the ability of that plant to complete its life cycle. So we can think about where these different nutrients come from, and what I want you to understand is, other than the structural ones, carbon, hydrogen, oxygen, those guys come from the air the plants breathe and the water they drink. Everything else, nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, iron, manganese, boron, zinc, copper, chlorine, cobalt, molybdenum, and nickel. All of those come from the soil, all right? So how you manage the soil and how we manage the fertility of the soil is darn important, because it makes all the difference in the world as to whether or not that plant is going to survive or not. Because everything, the ultimate source for those nutrients is the soil. So with that, we're going to shift gears a little bit and start thinking more in depth about things such as nitrogen and phosphorus. I'm going to turn it over to Dr. Osmond for a little while. Deanna's going to talk to you about nitrogen, the cycling of nitrogen, etc. So with that, Deanna, it's yours.
Thank you, David. I do want to talk about nitrogen because it is an incredibly important nutrient for the crop. As you saw from Dr. Krause's previous slides, it actually, except for leguminous species, is the nutrient most needed by plants to grow. And the reason it's most needed is it's involved in almost every single biochemical function that the plant goes through. It's part of the amino acid structure, which makes up proteins. It's part of the enzymatic processes, which change chemicals throughout the system. It's part of the DNA and RNA, and of course, if DNA didn't exist, none of the plants would exist. And last but not least, nitrogen is within the chlorophyll molecule. So it's incredibly important. The air that we breathe contains a lot of dinitrogen gas, N2, which is a very stable form of nitrogen. The problem is it's so stable that it mostly cannot be used by plants to grow. We'll talk about one exception to this. And again, nitrogen tends to be the most limiting nutrient when we're looking at crop production, because crops need nitrogen at such large amounts. The rest of this talk is going to focus around this slide that you see here, which represents the nitrogen cycle. One of the real problems with determining how much nitrogen crops need is, unlike phosphorus and potassium, calcium, magnesium, and even the micronutrients, we don't really have a good soil test that can tell us how much the plant needs. And the reason we don't have a good soil test is that the nitrogen cycle is highly dynamic. There are lots of gains to the system. There are lots of losses of nitrogen from the system. And all of these processes are going on at exactly the same time. So it's hard to know at any given point how much nitrogen is going to be available to your plants so they can grow well. What I'd first like to do is briefly talk about the gains and then the losses and show you what kind of numbers we're talking about. So without a doubt, as far as gains are concerned, most of the nitrogen that crops receive to grow well are either from commercial fertilizer or organic sources. And when I speak about organic sources, I'm not only talking about animal waste, but I'm talking about biosolids from wastewater treatment plants, manufacturing facilities, etc. Net mineralization, that's a second way that nitrogen is gained in the system. Net mineralization, it's shown down here, is how much nitrogen is released from the organic material in the soil, so that's the soil organic matter, minus the amount of nitrogen that is reabsorbed from this organic matter, which is releasing the nitrogen by the microbe community. So we have net mineralization, not just mineralization. Rainfall contributes some nitrogen. Depending on where you are, you'll get more or less nitrogen. And crop losses, the last gain is symbiotic biological nitrogen fixation. I appreciate Dr. Krause describing what this is. It's the plant's ability to use dinitrogen gas, which is generally non-reactive, and transform it into a reactive species of nitrogen that the plant can use. So those are our 4 gains. The losses come from crop removal and uptake. These can be very small or very large. Just because a crop takes up nitrogen doesn't necessarily mean it's removed. And if it's not removed from the system, it can be utilized by the crop at a later time, particularly in perennial types of crops rather than annual crops, because the nitrogen is translocated back into the roots and then used the subsequent year. And so when we're talking about crop uptake, in order to remove that nitrogen off the system, we're usually talking about crop harvest, such as removing the wheat from the wheat grain from a wheat crop. Denitrification is the second loss process. Erosion and runoff are a third process. Leaching, which is very, very important in our particular climate, where we have a very humid environment, is extremely important. And last but not least, volatilization. So when we're looking at gains, what kind of amounts of nitrogen are we talking about? Well, if you are indeed applying commercial fertilizer, about the least amount you can get on a crop is 5 pounds. Sometimes we go up as high as 280 pounds for our nitrogen fertilizer needs. There are few crops in North Carolina that would need more than 280 pounds of actual nitrogen per acre. This net mineralization process that I talked about, that is the release of nitrogen from organic matter decomposition minus the amount of that nitrogen that's reabsorbed by microorganisms, ranges anywhere from about 10 pounds on very sandy textured soils, which are low in organic matter, to upwards of 40 or perhaps even 50 or 60 pounds in organic soils that we have in North Carolina. So it's very much net mineralization is very much a function of the amount of organic matter that's in a soil, and that is related back to the texture. Non-symbiotic fixation is from microorganisms that don't need to be associated with plants but can still fix their own nitrogen. Typically the amount of nitrogen they put into a system is fairly negligible, less than 5 pounds per acre, and these are when pounds per acre is generally per year. Organic waste applications, again, and this can be manure or biosolids. It may well be over 200 pounds of nitrogen per acre per year. Rainfall typically in North Carolina adds anywhere from about 8 to 15 pounds of nitrogen per acre per year. It depends on your location. Folks that live near urban areas tend to get more nitrogen because of all the car emissions. Folks that live in more rural areas tend to get a little less unless there are a lot of animal facilities, and then you tend to get somewhat higher amounts of nitrogen from your rainfall. And last but not least, symbiotic nitrogen fixation in North Carolina typically ranges from 0 to 40 pounds of nitrogen per acre. That would be for a peanut crop or a soybean crop. If you get into something like alfalfa, and we don't really grow much alfalfa in this state, but there are a few places we do, you can get as much as 120 or 150 pounds of nitrogen from that alfalfa crop. So those are the types of gains we're looking at. When we look at our loss category, we see that crop uptake is really a function of many factors, and we'll talk about this more, but anywhere from 20 to 80% of the nitrogen that we put down is going to be utilized by the crop, and then we have to calculate how much of that nitrogen is actually in the harvestable portion. So again, if you have a wheat crop and you're removing the grain, you're going to remove some of the nitrogen, but some of the nitrogen will be left in the stover. Denitrification tends to be about a 10 to 20% loss of the nitrogen that you've put into the system. We don't have much nitrogen lost in erosion and runoff in North Carolina. It ranges from anywhere of 1% to 13%. Typically, it's less than 5%. That's not a major pathway loss for us. However, leaching is a major nitrogen loss pathway in North Carolina. We can lose anywhere from very little to leaching to over 50% of our nitrogen that we've added can be leached into the shallow groundwater. Now, if you remember back when we were talking about water quality, nitrate nitrogen in the shallow groundwater can be a health problem for humans, and it can also be a health problem for animals. The standard is that you cannot have more than 10 part per million or 10 milligrams per liter nitrate nitrogen in your shallow groundwater. And so if you have a lot of leaching, you may actually violate this standard of 10 part per million nitrate nitrogen. Last but not least, in some places they measure upwards of 40% volatilization. This depends somewhat on the fertilizer type that you're using and the placement. If you're using animal waste in North Carolina, you can get up to this 40% loss, although with commercial fertilizers we tend not to have nearly 40% loss of volatilization. This tends to be closer to maybe 1 or 2%. So again, the amount of losses we have, there is a range, and it's dependent on many different factors. Again, this is why it's so difficult to determine how much nitrogen you need in any given field for a given crop in a given year. So let's talk a little bit about the nitrogen forms. I want to go through the actual chemical symbols with you, show you what the name is, and show you where that nitrogen form is in the nitrogen pathways. So the first nitrogen forms that we're going to talk about will either be organic nitrogen forms, inorganic nitrogen forms, or gases. Organic nitrogen forms are tied up in the soil organic matter and the soil microorganisms. The organic sources that we actually put on the surface from animal waste or biosolids would also be organic forms of nitrogen. These are very complex, so I'm not going to show you any of the structures. They get broken down through mineralization, and they release inorganic forms of nitrogen. And then the inorganic forms of nitrogen can also be transferred and transformed to gases. So let's start by talking about the forms of nitrogen gases. The first nitrogen gas, and the one that we see most prevalently, is dinitrogen gas, which is N2. As I said earlier, it's not reactive, it's inert, and it makes up 78% of the air we breathe. This is both good and bad. Because it's not reactive, it doesn't cause any environmental consequences, but because it's not reactive, it typically cannot be used by the soil and crop system. So if you look at this box up here, let me get my hand working correctly, you can see that the atmospheric gases are mainly N2 with traces of NO, NO2, and N2O, as well as ammonia. So what do those gases mean? N2O is nitrous oxide. NO is nitric oxide. And NO2 is nitrogen dioxide. We tend to see more nitrous oxide than either nitric oxide or nitrogen dioxide. The problem with all three of these nitrogen gases is that they're greenhouse gases and they promote warming of our climate. So we want to make sure that if we're transforming our nitrogen in our soil system, to one of these nitrogen gases, we transform it to N2, which is an inert nitrogen gas. We also have ammonia. Now, I want to talk about this for just a minute because people confuse ammonia, NH3, with ammonium, NH4, which is a very important nitrogen form in the soil system. Ammonia is released through volatilization, and we talked about that earlier. And it comes from commercial fertilizers. Specifically, urea fertilizer is more problematic. So we have ammonia coming from volatilization. Animal waste tend to volatilize a lot of ammonia. Ammonia frequently is easily dropped out of the system in rainfall, and so it doesn't stay around too long, but it can be a problem, particularly for water quality. We're seeing a lot of atmospheric ammonia cause issues relative to water quality. So those are the nitrogen gases that we're dealing with. Some are produced through volatilization. I should have mentioned that these reactive forms of nitrogen gas come frequently from the emissions of cars. It will also come through denitrification, which we'll talk about later, but it's both an agricultural non-point source pollution as well as an urban non-point source pollution. Now I want to switch gears and talk about the plant available forms of nitrogen. We have two very important forms. We have nitrate, which is the predominant form of nitrogen that we find in a soil system, and we find ammonium, which is also prevalent in the soil system. Plants can use either nitrate or they can use ammonium. Some plants prefer nitrate, some plants prefer ammonium, some plants don't care at all. But they have different potential loss in the system through different pathways. And we'll talk about some of those losses and those pathways in just a minute. So let's talk about nitrogen transformation. This is where nitrogen gets really tricky and really difficult to determine how much nitrogen is in the system. Dr. Krause talked about symbiotic nitrogen fixation. And some plants, regular plants, use either the ammonium or the nitrate for their nitrogen source. But again, leguminous crops that have associated bacteria on the root system can utilize this inert form of nitrogen, the N2. They can split it and they can transform it to reactive forms of nitrogen, such as ammonium, that the plant needs. As Dr. Krause also talked about, what the bacteria gets from the leguminous crop species is carbohydrates. It gets energy. And so it's a symbiotic relationship. The plants need the legumes, the bacteria needs the crops. So one way of getting nitrogen into the system is through legumes. Now it's estimated that about 50% of all the nitrogen that gets into cropping systems comes from symbiotic biological nitrogen fixation. From an environmental standpoint, the amount of nitrogen from symbiotic biological nitrogen fixation has increased dramatically as we've grown more leguminous crops such as soybeans, alfalfa, clovers, etc. So one of the things that I want to mention is that sometimes people think that it's only nitrogen commercial fertilizers that are the problem vis-a-vis water quality, and it's not. Symbiotic biological nitrogen fixation probably contributes about 50% of all of the nitrogen that enters coastal waterways. So we need to think about this when we're thinking about the entire nitrogen budget. So how much nitrogen does these legumes actually add to the soil system? It is dependent on the species, it's dependent on the year, it may be dependent on the soil. So in North Carolina, these are the nitrogen availability coefficients that a working group put together. It shows that soybeans will add anywhere between 15 to 30 pounds of nitrogen per acre per cropping season, whereas something like the alfalfa will add anywhere from 80 to 100 pounds of nitrogen per acre in North Carolina situations. When I think about soybeans, I typically think that it's only going to add probably about 15 pounds of nitrogen. There's been plenty of studies that have shown that soybeans aren't real effective at adding nitrogen to the system. Peanuts, on the other hand, if I were to pick a number, I would use 40 pounds of nitrogen per acre per cropping season for peanuts. They do a much better job of adding nitrogen to the system. And when we talk about nutrient management later on, you'll need to remember these numbers. We actually have tables in your book that you'll be able to tag to have these numbers, because they're very important in determining the overall nitrogen budget of any given crop. So we've talked about addition from symbiotic nitrogen fixation, and I want to talk about some other processes that occur in the soil. As we discussed previously, oftentimes this nitrogen is released through mineralization, and it transforms to ammonium. Ammonium, as Dr. Krause discussed earlier, is a cation. It has the potential to absorb to the soil cations, to the soil particles, because they have anionic charges, and ammonium is held by the soil. It does not leach readily. On the other hand, it is transformed very quickly from this ammonium form to the nitrate form, particularly in our warm soils here in North Carolina. So ammonium is oxidized to nitrite through a bacteria that needs aerobic conditions. So it has to be an oxygenated system. These bacteria are referred to as nitrosomonas. This nitrite, NO2, is oxidized to nitrate. Now, the process from ammonium to nitrite to nitrate occurs very quickly. It's very difficult to find any nitrite in the soil system. There's another type of bacteria that transforms this nitrite to nitrate, Nitrobacter, and again, this is a very rapid process. So you see nitrogen in the ammonium form flipping to nitrate within a couple days in soils in North Carolina. We've seen this under field conditions, and we've seen this also in mineralization studies in the lab. So we just don't have a lot of ammonium in North Carolina. Even if the fertilizer that you apply is an ammonium-based fertilizer, or if it's animal waste that has real complex forms of organic nitrogen, they're broken down, they're mineralized to ammonium, and this is transferred very quickly to nitrate. This has important consequences for being able to hold nitrogen in our soils. Because most of the nitrogen in North Carolina soils is in the nitrate form, it can readily leach through the soil system into the shallow groundwater. This is some research that was done by Wendell Gilliam many years ago. In other research we've done recently, we see similar numbers. In a moderately well-drained soil, under a commercially fertilized field, we can see anywhere from 25 to 40 pounds of nitrogen being leached per acre per year. It's somewhat dependent on crops. We even see this, though, in particular situations for turf grass, for golf courses. And we've measured upwards of over 100 pounds of nitrogen per acre per year leaching under some organic agricultural systems. In our poorly drained soils, we tend to see lower amounts of nitrogen being leached, on the order of 10 to 20 pounds of nitrogen per year. It's not because less nitrogen is actually being leached in those soils. Rather, it's because these soils are waterlogged, and a process that we're going to talk about in a few minutes occurs, denitrification. And so a lot of the nitrogen that's being leached is transformed from nitrate to hopefully dinitrogen gas, but not always. Sometimes it is transferred to reactive nitrogen gases. And organic soils, you would think, would leach a lot of nitrogen because they contain so much organic matter, but in fact they only leach from about 1 to 5 pounds of nitrogen per acre per year. That's because these soils are very poorly drained and there's not much water movement in these soils. So we just mentioned denitrification, which is part of this whole nitrogen cycle that we're dealing with in the soil system. So the nitrate nitrogen leaches into the shallow groundwater, or it may even be in water-filled pore spaces in the soil. It's not necessarily something that just happens in the shallow groundwater. If you have low oxygen conditions in the soil, if you have carbon concentrations that are high enough, you will have denitrification. There are facultative anaerobes which can, under low oxygen conditions, under anaerobic conditions, transforms the nitrate into these nitrogen gases. And again, whether you have dinitrogen gas, or you have nitrous oxide or nitric oxide, it's a function of a complicated process. It depends on how much carbon you have, how anaerobic your soil system actually is, what the pH is, what the temperature is. The predominant nitrogen gas that is generated through denitrification is dinitrogen gas. So it's non-reactive, and that's what we want. We want to get this nitrate out of the shallow groundwater, and we want to get it back into the air as an unreactive form of nitrogen. But unfortunately, this doesn't always occur. Now, we mentioned volatilization a little earlier on. Again, if you apply your fertilizers on the surface, you have more chance for the ammonia or the urea, whatever the type, if you have an ammoniated nitrogen fertilizer, to be transformed to ammonia gas. If you use urea, there's more chance of the urea being volatilized into ammonia gas. Again, surface applied animal waste, the ammonia in those materials can be volatilized. If you put the animal waste, if you cultivate it into your soil, or you cultivate your fertilizers into your soil, or you knife your fertilizers in, or there are even some machines that'll knife some animal waste into the soil, you can really reduce your volatilization. The other thing that's really important is high pH soils and higher temperatures. These two conditions increase the rate at volatilization of ammonia gas. Here in North Carolina, as Dr. Krause described, our soils tend to be acidic. And typically, we don't want to lime our soils much above 6.3 or 6.4 because we start having micronutrient deficiencies. So typically, our pHs are low enough that we have very little volatilization. And I mentioned this a little bit earlier. We don't have more than about 1% or 2% of volatilization, at least with our commercial fertilizers. We can get upwards of much higher rates when we're talking about organic sources of nitrogen. So the ammonium that is produced in the soil can be immobilized by the plants or microorganisms. It can be absorbed. It can be bound to cation exchange sites, and I mentioned that earlier. It can be lost to the atmosphere as volatile gas, and so we talked about that process, volatilization. So the ammonium and hydroxide form to produce water and ammonia gas, and it can be oxidized to nitrate. So again, there are many pathways for ammonium loss. I would say the predominant form of loss in our systems in North Carolina is the oxidation to an anionic form of nitrogen, that is nitrate. As we talked earlier, ammonium flips very quickly in our soils to nitrate. So I want to get back to the nitrogen leaching losses, which I described as the primary loss mechanism for nitrogen in North Carolina systems. And the reason I want to talk about this is that it feeds right into our next discussion, which is how well crops utilize the nitrogen or organic sources that are put on. From the earlier slides, you saw that the majority of the nitrogen that enters the system that's utilized by the crop comes from either commercial fertilizers or organic fertilizers. We get a little bit from rainfall, we get a little bit from non-symbiotic nitrogen fixers, we get some from symbiotic nitrogen fixers, but without commercial fertilizers or organic sources of nitrogen, we'd have very little nitrogen in our systems. If our crop does not take up the ammonium and or nitrate, and typically it's nitrate in our soil system, it is lost through leaching into the shallow groundwater. And as we discussed when we were talking about water quality, this nitrogen leaches very readily through our shallow groundwater systems and into from our groundwater systems into our surface water systems. When you look at a system like the Neuse River Basin, they estimate that 70% of the water that flows in the Neuse River comes through the groundwater flow into surface runoff. Since we aren't losing much nitrogen through surface runoff, then we're losing most of our nitrogen through groundwater flow. So it's really important for our crops to absorb as much nitrogen as possible that we put in. And so I wanted to have this little prelude before we started talking about how well crops can utilize the nitrogen that we give to them. What is this percentage? Well, it depends. It ranges from anywhere between generally 20 to 80%. I've seen amounts that are lower than 20%. I've seen amounts that are greater than 20%. But typically, this is the range that we're looking at. The nitrogen use efficiency is a function of climate, soil type, crop variety, and nitrogen rate. And I want to show you some research that was done to give you an appreciation for how difficult that it is to figure out nitrogen use efficiency. And again, this goes back to trying to calculate how much nitrogen fertilizer we actually need for our crops. Now, I want to define nitrogen use efficiency. Everybody defines it a little differently, but let me tell you how I'm using it today. When we put a certain amount of nitrogen on a crop, let's say we put 100 pounds of nitrogen, we're adding 100 pounds of nitrogen fertilizer on that crop. Then we go out and we measure how much nitrogen that crop has taken up in its harvestable portion. That might be grain such as in corn, or it might be cucumber fruit as in the cucumber plant. And then there's always the stover or the vines. So we'll have the leftover corn stalks or we'll have the leftover corn vines. So we go out and measure the total amount of nitrogen in the harvestable portion and the portion that's left over, the stover or the vines. So in this particular example, let's say that we've got 70 pounds. Now, I'm not sure I know how to, I do. I found out how to do this. So we have 70 pounds, we've measured 70 pounds of nitrogen in the above ground portion of the crop that has had fertilizer put on it. We also have a control crop, and that control crop absorbs nitrogen, again in the harvestable portion and stover portion, but we've put on no nitrogen fertilizer. So it's only getting nitrogen from net nitrogen mineralization, it's only getting nitrogen from the rainfall, and we'll say in this particular instance, we get 20 pounds of nitrogen in the above ground biomass of the non-fertilized crop. Now we have put on 100 pounds of nitrogen for this crop. If you take 70 pounds, if you take 20 pounds from 50 pounds, you end up with 50. That's divided by 100. And you find that your nitrogen use efficiency is 50%. I can see why it's really hard to write with this little tool. This is a pretty good number. I would say that most trials that do nitrogen use efficiency see around 50% nitrogen use efficiency. Now, keep in mind that's for the entire above ground biomass. Only the corn crop, only the corn grain is actually taken off. Only the cucumbers are actually taken off. The nitrogen that's left in the stalk or the vines decomposes, it goes back into the soil organic matter. So actually the amount of nitrogen that you're taking off of this crop is always going to be less than the nitrogen use efficiency that you measure. So keep that in mind when we're thinking about nitrogen use efficiency. So we always have our nitrogen use efficiency on our y coordinates. It's a percentage. And in this particular instance, we have conventional tillage, we have chisel plow tillage, which is a form of reduced tillage, and then we have subsoiling. The subsoiling system goes down and it really breaks the plow pan so that the roots can go deeper. Now, Dr. Krause talked about this earlier, that the amount of rooting you have is really important because it determines how much water the crop can take up and therefore how much nitrogen the crop can take up. So they measured nitrogen use efficiency in this corn crop in 1978 and 1979. Although these data are pretty old, they're still completely valid. You can see in 1978 there was about 50 to 55% nitrogen use efficiency. I can't draw a straight line with this. Regardless of the tillage treatment, it was pretty much the same. There was really no statistical difference. But in 1979, nitrogen use efficiency was really low in the conventional treatment. It was only about 15%. When you get into the chisel plow, you get upwards of about 25%. And the subsoil, you get even higher. It's closer to 30%. The question is, first of all, why did you have lower nitrogen use efficiency in 1979 than you did in 1978? And why did the chisel plow and subsoil respond differently from the conventional in 1979 when they didn't in 1978? 1979 was a drought year. Water was extremely limited. When water gets limited, the ability of the crop to grow and absorb nitrogen also gets lowered. And so there was less nitrogen absorbed. Chisel plow and subsoil systems did a better job of breaking up that plow pan. It allowed the roots to get deeper, to absorb more water and absorb more nitrogen. So it's very much a function, nitrogen use efficiency is very much a function of climate. As you can see in this, climate was really the dominant, and it can be a function of how you manage that particular field. Some years management will be more important than other years. So again, we've got nitrogen use efficiency. This time we're looking at 3 different soils. We're looking at a Dothan, a Goldsboro, and a Portsmouth. Now the Dothan and Goldsboro are very similar soils. They're mineral soils on the coastal plain. The Portsmouth, however, is a mineral organic on the coastal plain. If you look at the nitrogen, there's one other thing about this particular experiment. They applied 50 pounds to some of their fields, 100 pounds to other fields, 150 pounds to additional fields, and last but not least, 200 pounds of nitrogen per acre. So we've got a yield response trial as well. Nitrogen use efficiency at 50 pounds of nitrogen for the Dothan and Goldsboro are about the same. We actually have about 60%, which is really great. In the Portsmouth, it's only about 40%. As nitrogen, the amount of nitrogen applied increases, we see that in the Dothan and Goldsboro, it's about the same or a little higher nitrogen use efficiency than we saw at 50, but the Portsmouth has started declining. At 150 pounds, we have even lower nitrogen use efficiency in the Portsmouth, and at 200 pounds, we have the lowest nitrogen use efficiency in the Portsmouth. I want to talk about this trend. Typically, the more fertilizer you apply, the lower the nitrogen use efficiency that you'll see. This doesn't always happen. I've got other data that it's not completely true, but in general, you use your nitrogen most efficiently when you're applying lower amounts of nitrogen. That is, you don't have excess nitrogen in the system to lose. The nitrogen use efficiency, if you look for the Dothan, it stayed pretty much around 65 the whole experiment. And yet, if you look at the Goldsboro, it went from about 60 down to about 50. And yet I told you that the Goldsboro and Dothan were very similar soils. The difference is the Dothan was irrigated. It never was water stressed. And so because it wasn't water stressed, it could use these high amounts of nitrogen. It could use the 200 pounds of nitrogen, whereas the Goldsboro couldn't use all the nitrogen that was available to it, and the nitrogen use efficiency declined. So the amount of fertilizer that you add is going to affect how much nitrogen your crop can use. Whether or not you manage it with water is going to determine how much nitrogen your crop can use. And last but not least, soil type. So again, this is why it's so difficult to figure out how much nitrogen your crop is going to use, you're going to need, because different crops, different climates, different soils need different amounts of nitrogen to be effective. Now, we already talked about nitrogen fertilizer rates being very important in determining how well your nitrogen is used. This experiment is a little bit different in that they looked at 112 pounds of nitrogen with nitropyrin. Now, nitropyrin is a nitrifying inhibitor. In theory, it's supposed to keep the ammonium from nitrifying to nitrate. So we talked about the nitrification step earlier on. So if we leave the nitrogen in the ammonium form, it should stay sorbed to the soil particles because ammonium is positively charged, and the negative particles of the soil are holding it in the soil. It shouldn't be as available for leaching, and theoretically, plants should be able to absorb this nitrogen better, and you should have a higher nitrogen use efficiency. So let's look first at the nitrogen rate of 112 and the nitrogen rate of 112 plus the nitrifying inhibitor. In both 1978 and 1979, there was absolutely no difference in nitrogen use efficiency. The nitrifying inhibitors, in fact, really do not work in North Carolina. We've seen this over and over again. But again, because we got more rainfall in 1978 than we did in 1979, nitrogen use efficiency was, nitrogen use efficiency was greater than it was in 1979. The second part of this particular experiment was the higher rate of 168 pounds of nitrogen per acre per year. And again, you can see the same trend that we talked about earlier, which is as nitrogen rates go up, your nitrogen use efficiency goes down, which means you have more nitrate in your system that can leach. And same way with the additional fertilizer applied in the 168 pounds of nitrogen. In the drought year, 1979, you also have a reduced amount of nitrogen being absorbed by your crop. Again, the whole reason that nitrogen use efficiency is so critically important is that if your crop's not using it, that nitrate's available to be leached through the soil system into the shallow groundwater and into our water resources. And as we talked in our first lecture, the whole point of nutrient management is, well, one of the major points of nutrient management is to protect our water resources. The type of variety that you use is really important as far as nitrogen use efficiency. Nitrogen use efficiency varies from crop to crop, but even within the same crop, it can vary. This is a tobacco experiment that was done in 1991. 50 pounds of nitrogen were applied to each particular tobacco variety. 70 pounds of nitrogen was applied, and 190 pounds of nitrogen was applied. The primary thing you see is that we've got 5 different tobacco varieties: Warren, NC82, McNair, Spite, G28, and K326. The Warren and the K326 were older varieties of tobacco. And the first thing that you notice is across all 3 fertilizer rates, the nitrogen use efficiency was only anywhere between about 35% to probably 30%. So these older varieties had less ability to use the nitrogen that was being applied. These newer varieties had closer to 50% nitrogen use efficiency, but not even quite topping nitrogen use efficiency. One of the things I said is that typically as we apply more nitrogen, you tend to see a lowered nitrogen use efficiency, but I also indicated that sometimes you don't. In this particular case, we got the best nitrogen use efficiency at 70 pounds of nitrogen, regardless of the variety that we were looking at. And in some cases, we even got as good of nitrogen use efficiency at 90 pounds. What this suggests is that we've never really over-applied nitrogen for these species of tobacco. One of the things that we did, because we had to for some regulatory requirements that had to do with water quality in North Carolina, is look at the nitrogen use efficiency of different crops by species. And I just throw this up to show you the difference in nitrogen use efficiency between species, and I had mentioned that previously. Bermuda grass, being a perennial, is the most effective at 75%, although do not assume that all perennials are more effective. There are some grasses that are perennial that have nitrogen use efficiencies that are as low as 30%. Because of the research database we had indication that we could split out nitrogen use efficiency by soil type, and I mentioned this earlier. Organic soils, sandy soils, which are arenig soils, do not allow as good of nitrogen use efficiency as coastal plain soils. Irrigated soils will have better nitrogen use efficiency because water is never limiting. And there's some indication that conservation tillage and the Piedmont may actually increase nitrogen use efficiency, although the information is anecdotal. And you'll see that other crops like tobacco, wheat, oat, rye, barley, and sweet potato tend to have lower nitrogen use efficiency than corn. And so with that, I will turn this back over to David so he can talk about phosphorus. And the last thing I'd like to say about nitrogen is because all these processes, as I initially indicated, are going on at the same time, it is very difficult to determine what the actual need of the crop will be, and we don't have a soil test. So when we get together in person, we'll talk about how we determine nitrogen fertilizer rates because of the uncertainty of all these processes occurring at the same time. And with that, David, I'm finished.
All right. Okay, so the good news for those of you that are going to be listening to this online, you are now almost halfway done with this soil chemistry and fertility review. I guess the bad news would be that you're only halfway done with this soil chemistry and fertility review. So if you haven't figured out yet, you can actually pause this presentation. There's should be a pause button down near the lower left-hand side of your screen. So what I'm going to do is I'm going to just take 10 seconds right here, turn my mic off, and give you a nice clean place to take a break and hit pause. Refill a coffee cup, do whatever you might need to do, and I will start back up in 10 seconds. Okay, for those of you that didn't take advantage of that 10 seconds, nothing like a 10-second break, huh? And for those of you that are coming back, welcome back again. And so where we're going to pick up now is with phosphorus and continue through the remaining macronutrients, phosphorus, potassium. We'll talk a little bit about calcium, etc., and then we'll hit on the micronutrients, and then we'll get into this discussion about fertility sampling and soil sampling. So phosphorus. Now, if you think way back when, earlier, we were talking about the macronutrients and the micronutrients and how some nutrients are needed at much greater concentrations than other ones. And phosphorus is one of those. You know, it's considered a macronutrient, but it's not considered, or it's considered a primary macronutrient at that. But it's certainly not used at the same rates or needed at the same levels as nitrogen and potassium. So we're talking, you know, 1/10 of it as much. When we think about phosphorus in the plant, really what we're talking about here is energy transfer and growth regulation. And, you know, you may have never heard of this chemical, ADP or ATP. Adenosine diphosphate and adenosine triphosphate. Those two things mean probably absolutely nothing to you. But what they do, actually, the words mean nothing, but they are very important to you because these two chemicals are responsible for the transfer of energy within your body and within plants. The ADP, ATP kind of thing. And so what, again, the names, adenosine diphosphate and adenosine triphosphate. Phosphate, P. Oh, hey, phosphorus is probably pretty important with regards to how energy moves around. You know, when we start talking about converting sunlight into sugars and things like that. So, you know, phosphorus is critical in the energy transfer within the plant, and thus has a lot to do with the regulation of growth in the plant. It tends to be concentrated in seeds and fruit eventually as a place or a mechanism for that phosphate to be carried over to subsequent crops. The deficiency symptoms can be quite striking. In fact, if you look at this plant here on the right, this is an example of a phosphorus deficient corn plant. And you see that it's purple. And as you can imagine, purple is probably not a color that you want to see in your corn. You probably want your corn to be green. All right. Well, this is fairly typical of this phosphorus deficiency. The good thing about these phosphorus type of deficiencies, in this case this purple one, is that, you know, they occur in early season in cool weather and sometimes can actually grow out of these systems or situations as temperatures warm up and mineralization starts to occur and phosphorus starts to be released from the soil, etc. You can also result in abnormally dark green plants. Now, how can this happen? Well, if a plant, because of the phosphorus situation, is stunted, you know, you may have a lot of chlorophyll that's actually packed into a smaller plant. Now, what is chlorophyll? Chlorophyll is that organic compound that transfers light energy into chemical energy. It turns sunlight into sugars, all right? And so if you've got a lot of chlorophyll, packed into a smaller area, you end up with a much darker green type of leaf. So abnormally dark green can also be an indication of phosphorus deficiency. Now, typically when you see these abnormally dark greens, you see a much, a stunted plant. So this warming, we talk about you can grow out of a phosphorus deficiency, and really what we start thinking about here is this concept of the phosphorus cycle. Now, Dr. Osmond spent quite a bit of time going through the various pieces of the nitrogen cycle, where you talked about leaching losses, you talked about transformations of gas forms to to other inorganic forms, and inorganic forms to organic forms. So you heard terms like mineralization and mobilization, things like that. Well, the phosphorus cycle has a lot of those same processes kind of occurring, but there's some that really don't happen. We do not have gaseous forms of phosphorus that we consider in this world of soil science. We don't have volatile losses of phosphorus, and although we have phosphorus leaching, we have much lower concentrations of phosphorus leaching. So I want to think about the phosphorus cycle from a little bit different perspective. What I want to think about is organic sources, so things that are in this kind of area, and inorganic sources, so things over here in the fertilizer world. All right. So in both cases, organic sources or inorganic sources, where a material is applied to the surface of the soil, you have a couple of different pathways of where that material can go. So we come down and the fertilizer goes into a stable, unavailable pool of phosphorus, or it goes into something we call the soil solution. Now, what is the soil solution? Soils essentially are made up of mineral matter, organic matter, and pore space. That's the place where you have neither minerals or organic. So it's like the pore on the skin. It's a place where gases can exchange. It's a place where water can accumulate, etc. So we think about the soil solution. What we're talking about is phosphorus that is dissolved in the water that is in the soil. All right. So fertilizers can contribute to this soil solution pool of phosphorus. At the same time, they can contribute to this unavailable phosphorus pool, this stable pool, if you will. Now, over time, a plant takes nutrients out of the soil, and the plant takes nutrients out of the soil in a liquid form. The nutrients all, for the most part, get in the soil nutrients get into the plant through the water that's moving into the plant. So as the plant takes up water, it takes up nutrients out of this soil solution phosphorus pool. So the concentration in soil solution phosphorus will go down. Well, that triggers an equilibrium type of reaction. So what this arrow here indicates is that this soil solution pool is trying to remain at an equilibrium, or a steady state, if you will, with the stable phosphorus pool. So as you remove soil solution phosphorus, this equilibrium, let me get rid of this one too. As you remove soil solution phosphorus, this equilibrium shifts in this direction, and phosphorus transforms from that stable pool into the soluble pool. That soluble pool then goes back into the plant, and that shift continues even further in that direction. All right, so let's go back and think about this concept of the stable pool for a minute, and the shift in the other direction. So we fertilize, and nutrients come down from the plant, from the fertilizer down this pathway, right? So down that pathway into the soil solution, and the soil solution concentration gets greater than what its equilibrium with the stable pool would like to be at. So in that case, the soil solution phosphorus goes in this direction and contributes to that stable, unavailable phosphorus pool. All right? So the same thing happens when we think about organic materials, where we have organic materials contributing to the soil solution P. We have organic materials contributing to this stable form of phosphorus. We have the equilibrium going from the soil solution P to the stable form, and then we have the equilibrium shifting back as things are pulled out of the solution, if you will. Now, one thing I want to point out, if you look at the issue of phosphorus leaching, what you do not see is phosphorus leaching out of this stable pool on either side. You know, these are relatively tightly bound mineral forms or tightly bound organic forms. When we start talking about phosphorus leaching, what we're really talking about is leaching of that phosphorus compound that's in the soil solution. And I guess, you know, let's think back to the way we've used these kind of diagrams before. The fatter the arrow, the greater the loss, or the greater the amount of material being moved through that pathway. And so what you see is, let me clear all these guys out here and get us a nice clean screen. A relatively large arrow, a somewhat smaller arrow, and an even smaller arrow. So you get the idea that phosphorus leaching is really not that big of a loss pathway. We start thinking about phosphorus cycle. What do we see that we're missing up here? We don't see a volatilization loss, correct? So that's not an issue. We do see a runoff loss. Now, we'll talk about this more in a few more slides and then greatly expand on it in a few weeks. When we start talking about phosphorus loss assessment tool. When we start talking about the phosphorus loss assessment tool, really what we're talking about is how can we manipulate the cropping system, manipulate the best management practices that we have out there, manipulate the fertilizer or organic sources to really control the thicknesses of these arrows. And one of the arrows that we're really going to be concerned a lot about is this runoff phosphorus arrow. So that's essentially the phosphorus cycle in a nutshell. Now, when we start thinking about phosphorus cycle, you know, one of the things that we can think about is the impact of pH. And we've talked about this earlier about iron, aluminum, and calcium when we're looking at the availability of those nutrients as you change the pH of the system. And so when we start thinking about southeastern United States soils, you know, we're looking for somewhere in the 5.5 to 6.5 pH range in order to give us the maximum availability of phosphorus. And so let's kind of fast forward, if you will, to a graph and kind of see if we can figure this out. So this graph kind of gives you a distribution of where is the phosphorus in the system. Is it in some sort of chemical fixation with iron and aluminum? Is it, you know, bound up by some sort of iron and aluminum mineral? You know, is it perhaps tied up in calcium minerals, etc.? Or is it freely available in that soil solution? All right, and that's what this lower peak is showing, or lower graph is, or part of the graph is showing. So in the North Carolina type of systems, you know, we are trying to lime somewhere in this range right there so we can achieve perhaps the maximum concentration of available phosphorus in the solution. What are we talking about? Well, what we're talking about is manipulating the soil pH, if you will, in order to make this pool over here. So we're going to try and make this bubble a little bit smaller, and we're going to try and make this bubble a little bit bigger. All right? So that's what we're trying to do with pH, is change the size of those two particular bubbles. So North Carolina system, or southeastern United States system, what we tend to see, you know, we have a lot of iron and a lot of aluminum, and so by far the vast majority of our phosphorus is tied up in these iron, aluminum, and mineral kind of complexes. So you have very little of that stuff in solution, so that very little of this leaching loss right here happens. All right? So what are we talking about as far as concentration? So let's go back and think about our bubble, if you will. Our two bubbles. You have the stable pool that kind of represents the total phosphorus. You have the soil solution pool that kind of represents, there's our soil solution pool, that kind of represents that center bubble. So there's our stable pool, there's our soil solution pool, okay? Now what we don't have listed on this particular graph is there's actually, you could divide this stable pool into stuff that can easily be broken down and easily become plant available versus stuff that is really, or phosphorus that is really difficult to make available. So for the purposes of that, let's kind of draw a dotted line down through there or something. So this may be our plant available. Over here is our, highly unavailable kind of thing. So back to our concentration. So if you're thinking 1,000 parts per million versus 0.01 part per million. Now let's put this in perspective. 0.01 part per million, the amount of phosphorus in solution. 0.01 part per million would be just about like taking an eyedropper full of food coloring and squirting that into a tanker truck or a tanker on a train somewhere. One of those big tank cars on a train. I mean, it is a really, really dilute solution, the phosphorus. But when we start thinking about water quality implications, it doesn't take a lot of phosphorus to cause water quality problems. And Dr. Osmond mentioned this when we were talking about nutrients and water quality, how low of concentrations you really need in order to trigger these type of algal blooms and that ultimately lead to fish kills, etc. So we need to think about how does soil test phosphorus change as you add phosphorus to the system. And the reality is, it changes pretty slow. And it has to do with the fact of the size of these bubbles, okay? So we go up here and we add fertilizer, and we get a lot of fertilizer that comes down into this stable pool. And then some of that stable pool shifts over to this plant available pool, which then shifts over to this soil solution pool. So in general, it takes about 8 pounds of phosphorus per acre in order just to increase this pool down here by 1 part per million. Oops. Now, so let's think about North Carolina for a minute, because that's where we're located and we're really interested in. Typically, our southeastern soils, high in iron, high in aluminum, they have this tremendous ability to hold on to that phosphorus, to pull it out of the soil solution and bind it up in those stable systems, those stable soil systems. And we've continued to fertilize our soils in North Carolina due to tobacco production and due to animal waste management type of applications. And what we're starting to see is that these iron and aluminum, concentrations are able to hold on to all this phosphorus, and we're starting to see our phosphorus levels in our soil come up quite a bit. And so what we're looking at here is this particular map. You're looking at two different shading schemes here. You've got kind of an orange, peach kind of color, and you have this kind of mauve, light red or something like that. North Carolina has what we call a phosphorus index system, and we'll look more at the phosphorus index in a few slides. But the way the index system works is essentially if you're above 50, in that 50 to 100 range, you don't need a lot of you don't need a lot of phosphorus to be applied. The crop is not going to respond to it. If you're above 100, you certainly don't need any phosphorus to respond there. All right, and so we're trying to get you to get a feeling for here. The average index for all the crops in those particular soils. So if you look at the average soil test in Wake County, for example, what you see is that our average phosphorus level is above 50. If you look at some of the counties where we have a lot of animal agriculture, Sampson, Duplin, Wayne, Moore, Montgomery areas, up here Wilkes, we've had a lot of phosphorus go out in the manures, and so these soils in those counties are getting even higher levels of phosphorus built up in them. So let's go and look at the national perspective for a minute, if you will. And this is from a 2001 soil survey, where basically we're trying to get a grasp for, how are we doing on phosphorus fertility. And what we're seeing here is that, in North Carolina, 31% of our soil samples test low or medium in phosphorus. There's a way to think about this in the inverse. 31% test medium or lower, or 69% of them test higher than medium. Okay, so we have got an elevated soil phosphorus level in this state of North Carolina, which is exactly why we're having this discussion about phosphorus and why we're going to have this discussion about the phosphorus loss assessment tools, because we are building up our levels of phosphorus in the soil that can become a long-term problem for us with regards to water quality issues. Well, in order to think about how long-term of a problem we have, we need to think about how much phosphorus is being removed by a particular crop. Now, go back and think about something such as a Bermuda grass crop, where we're putting out 200, 250 pounds of nitrogen. Now, some of our waste products that we put out has, for every 1 pound of nitrogen, you have 1 pound of phosphorus. So if you put out 200 pounds of nitrogen, you may be putting out 200 pounds of phosphorus. But remember, our crops only take off or only need 1/10 of as much. So if you put out 200 pounds of phosphorus and you only needed 20, you exceeded your phosphorus needs by 180 pounds. So you're continuing to drive this number right here lower and lower. So we're no longer 31, we're now 30. Now 29% of our samples test low, 28%, 27, all right, as we continue to build the phosphorus levels in our soil. And so what we have is this concept called phosphorus takeoff, phosphorus removal. And these are just some examples in this chart of, I picked a particular soil and looked at the yield values and looked at how much phosphorus per unit of yield would come off for a particular crop and calculated the phosphorus removal value. And so you get the idea that, hybrid Bermuda grass has our highest, or one of our highest, phosphorus removal rates. Actually, our highest phosphorus removal rate is sorghum Sudan hay at 87 pounds of P2O5 per acre. Now, look around North Carolina and you don't see a lot of sorghum Sudan hay because the management of it is a lot more time-consuming than something like hybrid Bermuda grass hay. The take-home message from this particular slide is that, let me clean it up a little bit. The take-home message from this particular slide is that not all crops have the same phosphorus removal per unit of yield. And not all crops, so let me pick some that are all tons. So here, phosphorus removal per ton of yield, phosphorus removal per ton of yield, phosphorus removal per ton of yield. All right. So in that particular case, fescue has the highest removal rate per ton of yield. But the other thing we need to consider is, what is our potential yield? And so we see that fescue hay only has 3.5 tons of potential yield. Hybrid Bermuda has 6.5 tons of potential yield versus common Bermuda has only 5 tons of yield. So the factor of phosphorus removal rate is a combination of yield and the takeoff value, the P factor, if you will, P take-up. So I mentioned that we're heading down this path of long-term problems. And what we have here, this is a study from Dr. Gene Camper, published in 1999, where we're looking at the Lynchburg soil, and they're growing a corn and soybean rotation on this particular soil. And on the site, they started with phosphorus index values somewhere in the 140 to 160 range. And they applied either no phosphorus, oops, let me switch pointers here. They applied, there we go, no phosphorus, 10 pounds of P2O5 per acre, 20 pounds of P2O5 per acre, or 40 pounds of P2O5 per acre, and just looked over 15 years what happened to the phosphorus values. And so you see, starting out here, You see, starting out here in year 0, today, if you will, what the values were, and then 15 years from now, what the values were. And the thing that you can really pick up is, as you go through time, when you add phosphorus, oops, let me change it. When you add phosphorus, come on, there we go. Here, when you add phosphorus, 40 pounds per acre, you can kind of maintain your phosphorus levels in the soil. When you don't add phosphorus, you can get a decline in the amount, all right? And so in this case, what we see is over a 15-year period on this particular cropping sequence of corn and soybean rotation on the Lynchburg soil, we went from about 160 index down to somewhere around, I don't know, 90, 95, something like that. So we had a 65 unit, a 65 unit, no, a 65 unit. Boy, my math is horrible today. So we had a 65 unit drop, if you will, in the index values. So, is that a good thing? Yeah. We see that we can, without making further applications, we can start pulling the phosphorus levels down in our soil. Now, there's a couple things to point out on this particular slide, all right? This is the point right here at which, no more phosphorus applied. Down here somewhere at 50 is the point at which, we wouldn't make any phosphorus recommendations because the crop wouldn't necessarily respond to those phosphorus recommendations. That gets into the index system. Again, we'll talk more about that in a minute. Thing I want to point out, though, is that we are still well above that range 15 years later of where you would actually start making fertilizer recommendations for this particular crop. Another thing I want to point out on this particular slide, right? This is not your typical animal operation. Your typical animal operation may be up here somewhere. So let me extend our graph, and let me write in some numbers for you. 300, all right? And so our start point is up here somewhere, and over 15 years, we go down the same rate. Where do we end up? Oh, we're down there around, 240. So we've got a long ways to go to get that sample, to get my pointer. We've got a long ways to go to get that sample right there back down to a range down around here somewhere where phosphorus, the crop will respond to that phosphorus. We have got a tremendous reserve of phosphorus in this system, all right? We have built up, let me see. Nope. We have built up, one more. We have built up these stable pools of phosphorus right here. So that bubble right there, instead of being that size, that bubble is that size. It's huge, okay? And it's going to take us a long, long time to shrink that bubble back down to this much smaller size. So let's fast forward again. All right. So this slide right here kind of summarizes what we're going to be talking about with regards to the phosphorus loss assessment tool. And that has to do with the fact that, we have these different loss pathways. We have runoff of soluble phosphorus. We have erosion losses of clay and sediment that carry phosphorus bound to it. And we have these leaching losses. You can have some organic leaching forms, some inorganic leaching forms, etc. But again, the whole concept of the fatter the arrow, the greater the loss pathway. So you get a feel for where we're losing a lot. And I don't want to spend a lot of time on particularly this slide because it will really steal a lot of thunder from the phosphorus loss assessment tool that we're going to be talking about later in the training program. Just recognize that we have different mechanisms by which we lose phosphorus in our soils. Some of them account for greater losses, such as erosion with erosion of particulate matter with phosphorus bound to it, and then also erosion or washing or runoff of soluble phosphorus forms. And so that kind of introduces this concept of the phosphorus loss assessment tool. what we refer to as PLAT. You know, where it has 4 loss pathways considered, where you have the particulate phosphorus, you have the dissolved phosphorus, you have leaching. So you have particulate soil phosphorus, dissolved soil phosphorus, you have leaching losses, and then you have sources from the dissolved portion of the phosphorus fertilizer material itself, whether it's manure or something like that. You know, it looks into things like the soil test phosphorus value, erosion using the revised universal soil loss equation, looks at drainage issues, etc. And so basically what we're trying to do is put together the pieces of the puzzle here, which looks at not only these loss pathways, but how big are the bubbles, how big are the pools of phosphorus in the soil, so we can calculate whether or not a particular site is at risk of causing us some problems later down the road, or further downstream, literally, from a water quality perspective. So let's shift and think about potassium for a minute. The third of the primary micronutrients, macronutrients I should say. And you know, again, this one is required, potassium's required at about the same amounts as nitrogen, it's nitrogen, which means it's about 10-fold the amount of what's needed for phosphorus. From an environmental perspective, you know, we really don't know of any, you know, potassium problems associated in the environment. You know, what is it used for in the plant? Well, it's a key component of photosynthesis. It's a key component of water regulation and protein synthesis. And so it kind of works into drought tolerance, disease resistance, things like that. How is it a component of water regulation and drought tolerance? Well, these little cells on the bottom of a leaf. Now, leaves have these things called, well, let me draw you a little plant. So we have a plant. All right, here's our roots. Here's our tree. All right. And in general, water moves through the roots, up through the stems, out the leaf, and then out into the air. All right. And it flows through the leaf through this pore called a stomate. And the stomate is nothing more than like the sweat glands on the bottom of your armpits, if you will. It's a hole in the plant. And what controls the opening and closing of that hole, of that stomate, are these 2 guard cells that surround it. And so they're kind of like kidney bean shaped. They're like that. There we go. So that'd be an example of stomates are open. This would be an example of stomates are open but not quite that much. And this might be an example of the stomates are completely closed. Alright? So here's our hole, and there's our hole, and then there's no hole in this third one. And what controls these guard cells opening and closing is potassium. As you the plant pumps potassium in these cells, it changes the salt concentration, which causes water to move in or move out, causing these things to swell up, kind of like a balloon. All right. So here you have swollen balloon. Here's a balloon not quite as swollen. Here's a deflated balloon. All right. So the potassium affects the water regulation, water movement in the particular plant, which means it affects drought tolerance. With regards to disease resistance, what we're talking about here is that the potassium has a lot to do with the strength and integrity of membranes and cell structures, and so making them more or less resistant to being attacked from disease organisms. Now, when we start thinking about where is potassium in the soil, it really comes back to this guy. Remember what that is? Yeah, that's our clay particle, all right? And what are these things? Those guys right there, there's our negative charge. And all these negative charges make up what? Our cation exchange complex, right? So where's our potassium? Our potassium is stuck right there on these exchange sites for the most part. You know, there are other places that it can be. You know, we do not talk about clay minerals much, where you have, you know, these aluminum layers and these silicon layers, etc. but you can end up with potassium wedged deep inside of the actual chemical structure of clay minerals. So, as I said, we're fortunate that we, to my knowledge, there's really no known environmental issues associated with potassium. It's not like if you have a lot of potassium in the soil, you can expect a major fish kill or algal bloom downstream. So one of the things we need to think about is the fact that, the types of nutrients used by a plant relative to the elemental symbol of that nutrient versus how it's determined in a bag of fertilizer. Now, when we talk about phosphorus, we talk about P, or we talk about K, potassium. But a plant does not use the elemental form of phosphorus. What is the elemental form of phosphorus? I mean the phosphorus as it would exist on the periodic table of chemical elements, right? It doesn't use that form. It uses this H2PO4, or it can use let's see if I can write this, HPO4 2-. So HPO4 2-. It uses that one as well. But primarily it prefers H2PO4 minus. Now potassium uses K+. Now when you go out and buy a bag of fertilizer, and we'll talk about this when we get to fertilizer sources once you get on site at the training session. So you buy something that is 10 fertilizer. What are you buying? You're buying something that's 10% nitrogen. It's 10% not P, but P2O5, and 10% K2O. All right. So there are cases where, depending on, there are cases where you need to convert elemental phosphorus to P2O5 in order to understand what's happening in a particular system. Now, in our fertility recommendation models from the North Carolina Department of Agriculture and Consumer Services, all that's happened for you, all right? And we'll talk more about those fertilizer models here in about 2 slides. But the point being is if you need, for some reason, to convert a pound of P2O5 to actually how many pounds of P are out there, the conversion is, 1 pound of P2O5 equals 0.44 pounds of P. Flip side of that is 1 pound of P, 1 pound of phosphorus equals 2.29 pounds of P2O5. So 1 pound of K2O equals 0.83 pounds of K, and 1 pound of K equals 1.2 pounds of K2O. So these are just conversion factors that you can use should you ever have to flip back and forth between, the amount of phosphorus and the amount of P2O5 you need. Now again, if you're working in soils in North Carolina running your soil samples for your fertility models through the Department of Agriculture, it's not going to be a problem for you. So that's a good transition for us to start talking about these phosphorus and potassium recommendation models. In North Carolina, when we start thinking about soil fertility, we think about something called a sufficiency approach. And the idea behind that is that we want to provide enough nutrients there for the plant to meet its needs, but yet not over-apply nutrients that may be costing us economically. Now this is a completely different concept than the way that they work in some of the Midwestern states. In some of the Midwestern states, they treat the soil more like a bank. And so when prices of phosphorus are low, they may go out and put not only the amount of phosphorus they need for growing this particular crop, but the amount of phosphorus they may need for growing crops for the next 3 or 4 years. When they think about potassium, they may do the same thing. We're going to apply for potassium for this crop plus the crops for the next 5 years. And it all has to do with, they're banking their nutrients in the soil. Here what we're trying to do is do an approach of, a more environmental approach of, feeding the soil that's going to feed the crop, but at the end of the cropping season, there shouldn't be many nutrients left over. So it's a sufficiency approach, if you will. Now, we start thinking about fertilizer recommendations. We work off of a model where we have what we call diminishing returns, right? we may be able to hit 100% maximum yield. But getting from 95% yield to 100% yield is going to be quite expensive. All right? So follow me here on this slide for a second. So this is our crop response. Let's see, our relative yield and the amount of phosphorus, or amount of nutrients that are applied. So if we have a soil that has a 60% yield and we add some nutrients, you know, we're going to eventually reach, you know, 100% yield. Or if we have 20% yield, add some more nutrients, we're eventually going to reach 100% yield. What you see on this slide, though, is that this black line right in here. So that black line represents kind of our 95% level. What that means is that the effort it took us to get from 60, wrong pen. The effort it took us to get that 60% yield from 0 to 95 is just about the same amount of effort it takes us to get from 95% yield up to 100% yield. Okay, so we have to work equally as hard to get that last 5% of the yield. So from an economic perspective, it makes no sense to fertilize for that last 5%. You know, we'll shoot for a 95% kind of yield. So that's the way we've developed our fertility recommendation models in the state of North Carolina. The other thing that you see is, you know, other than we're not shooting for 100% yield, is if you have a soil with relatively low yield potential, you know, it takes more fertilizer to get to that 95%. And if you have a soil with a relatively, you know, higher yield potential, all right? So this is basically getting you at the concept of low fertility soils versus low fertility soils versus medium fertility soils versus high fertility soils. The other thing that comes out of this particular graph is if you have a high fertility soil, you don't need to apply any fertilizer whatsoever in order to achieve that 95% yield that runs right along through here, because you've already reached that capacity. So this is that sufficiency type of model. And the way it works is that the amount of nutrients that are available in the soil, we can graph the amount of nutrients available in the soil relative to the pounds of fertilizer that are needed. So if we have a high concentration of nutrients in the soil, we need 0 nutrients applied in the form of fertilizer. If we have a lower concentration of soil nutrient, phosphorus, potassium, whatever, you know, we need a different amount of nutrients applied. The same goes, you know, even lower, you know, you get the concept here, all right? So basically what's happening with this particular graph is as soil nutrient concentration goes down, the amount of fertilizer nutrients needed goes up, all right? Another way of thinking about that, as soil nutrient concentration goes up, the amount of fertilizer nutrients you need goes down. And this is the whole concept behind the NCDA Agronomic Division Soil Test Index system, is that we're trying to relate the amount of nutrients we need to apply relative to the nutrients that are in the soil, and relating those nutrients in the soil back to whether or not we will see a crop response. So the high soil nutrient status versus the medium versus the low. All right. So these are the index values, and there's kind of a prediction system. You know, what we've done here is not developed a prediction system from an environmental perspective, but we have developed a prediction system from the likelihood of a crop responding economically to that fertilizer. Meaning, if you spend $1 on that fertilizer, are you going to get $1's return back for that particular fertilizer? Or are you only going to get 75 cents back or something like that? So the soil test index system, and this is a table basically summarizing the whole soil test index system, where you have an index of 0 to 25, gives you a low rating, which means if you put phosphorus out there, there is a high probability that that crop is going to respond to that phosphorus being applied. If you put potassium out there, there's a high probability of it responding to that potassium that's being applied. And if you put copper and zinc out there, there's a high probability that that plant will respond to that copper and zinc that was applied. Now, if you have, 20, let me change colors. So if you have 26 to 30 out, or 26 to 50 out there, that gives you a medium rating. And basically what's happening is you get this, well, the plant's going to respond, perhaps. It may or may not respond, but you should probably put this out there because we're getting in a questionable area as to whether or not that particular nutrient is a deficient nutrient. All right, and that's the way the phosphorus and the potassium models tend to work. Copper and zinc, above a 25, you get a recommendation back of no, don't put any out there. There's no need to. When you get into the 50 to 100 range, there's going to be no response to the phosphorus or potassium you put out there. When you get above 100, there's certainly going to be no response to the phosphorus that's put out there. But let me back up and talk about this range right here. There will be instances on a soil test report that you get back from the North Carolina Department of Agriculture and Consumer Services soil testing lab where you have an index above 50 where you actually will get a recommendation. And you ask yourself, well, why? We're not going to get any kind of crop response to that. And the thing that they're trying to accomplish with that recommendation is basically putting back the nutrients that you're going to take off. So your soil is in one of those questionable levels to where if you've got index that's marginal, somewhere around 60, and you grow a really high yielding crop, you may pull enough phosphorus out of that particular system to drop that index value down to say a 48 or something like that. And so you have to kind of replenish what you remove. So you will still get recommendations from these 50 to 100 range that are you're not going to get a response to them, but you're just kind of replenishing what you're going to remove so you don't hurt the subsequent crops. Oops. Now, as I mentioned, all this stuff kind of fits this quadratic model, or this model right here. This is a curvilinear kind of deal. All right, and if you know anything about math, that follows a formula of ax squared plus bx plus c equals, I have no idea. All right. Well, the thing that we can think about from a soil fertility recommendation model is that we can replace that x squared, or that x, if you will, with some sort of value that is relevant to the soil concentration. So our soil index, for example. So we end up with something like A times the soil index plus B times the soil index plus C equals how much fertilizer we need to apply. And in fact, that is the very model that we use in North Carolina. So there are over 90 crops, or the most common 90 crops in North Carolina fit one of the 25 set of coefficients below. Everybody is working off of the same AX plus index squared plus B, A times the index squared plus B times the index plus C. It's just a matter of what do we use for our A, our B, or our C. And here it is. There's our A, there's our B, there's our C. There's our A, our B, our C. And so for some crops, for phosphorus, for example, it says use equation 14. And for potassium, use equation 16. For other crops, it may say use equation 23 and use equation 8 or something like that. So all we're doing is playing games with this same exact A index squared plus B index plus C equation. We're just changing our coefficients. All right. So let's go through an example here now. Now, phosphorus is an interesting one because phosphorus, remember, phosphorus is bound up with aluminum and iron. So what happens when you get into an organic soil where you don't have a lot of aluminum and a lot of iron? You completely change how that phosphorus behaves in the soil. And so for phosphorus recommendations, we have, in some crops, we have different models, different equations, different ones of these, if you will, depending on whether or not we're in an organic soil or an inorganic soil. So let's look. Here we have organic matter is greater than 5.3 versus organic matter is less than 5.3. So what that means is, based on that soil class, is it a mineral organic, or an organic soil, we either use this set of coefficients or this set of coefficients to determine our phosphorus level. Alright? So, here's our example. We're making a corn phosphorus recommendation. We have a p-index of 32 and a humic matter of 6.2. Humic matter of 6.2 means that we're going to use equation 15. So we're going to use that guy, alright? Equation 15. So we go back. So phosphorus recommendation is going to be 0.0227 times 32 index squared. Where's that 32 coming from? There you go. Here's our 32. Where's that 0.227 coming from? 0.227. Oop. Where did it come from? Actually, you know what? This should say equation 16. Yeah, that's the coefficient coming out of the equation. That's the coefficients coming out of the equation. And that is the coefficient. So you do the math, and what you figure out is you have 32 pounds of P2O5 per acre required. Now, why am I spending the time of going through this? Okay, so let's say you decide to, in a nutrient management plan, you're going to plan for soybeans, or plan for, I don't know, sorghum. You're going to put sorghum out there, all right? But all of a sudden, so you write your plan for sorghum based off of this, or you come up with your nutrient applications based off of sorghum crop as the crop, receiving crop, using a soil test that you submitted to the Department of Agriculture. Okay, so what if sometime after you come up with your fertilizer recommendations, the price of corn just goes through the roof, and you decide that you're going to go corn and grow corn instead of growing sorghum? Does that mean that you need to resample that particular field and submit that sample again and wait for that sample to be analyzed and come back and get the recommendations? And the answer to that is no. The reason being is because you have your index and you have your organic matter, right? So all you have to know is which one of these equations would you use to now solve for your corn as opposed to your sorghum. And so we're going to do that one, right? So we'll change and use that coefficient, or use that set of coefficients, or it just so happens that we need to use this set of coefficients or something like that. So we have the ability now, knowing how to use these models, to save ourselves, days, and in some cases weeks and weeks of time, simply by taking our existing soil samples and recalculating our recommendation models. Now, potassium works the exact same way. This is potassium recommendation for cotton. It's not dependent on organic matter. So cotton says use equation 13. So, here's our equation 13 right there. So if we had an index of 78, there's our equation, our recommendation model. So what is our recommended amount? Well, one thing you can think about is, remember, we're working off of this. Ooh, boy, that's a horrible looking square. So we're working off of this particular table right here, right? Where we're trying to figure out what. Oops. So we're working off of that guy, right? So we have a measured potassium index of 78. Can we not quickly and easily look at that measured index of 78 and say, oh, hey, we're in that 51 to 100 range. We probably don't necessarily need any. There's not going to be any phosphorus recommended, perhaps. All right. Yeah, so that's one way to kind of save yourself even more time. Look at that K-index, see a 78, you go, well, that's going to be 0. Why? Because it's not going to be responsive. All right. So let's move into the secondary and micronutrients for a little bit and think about those. When we think about secondaries, we think about the secondary macronutrients. We can think about calcium, magnesium, and sulfur. You know, these guys are all critical to plant growth, but often are not considered as important as nitrogen, phosphorus, and potassium. You don't hear people talking about going out there and having to do calcium fertilization or magnesium fertilization. And the reason for that, at least in North Carolina, is because we get a lot of calcium and magnesium coming in through our lime sources. We have these low pHs, 4.5 to 6.5, right? Or 4 to 6, somewhere around there. And so we're constantly liming, and so that's giving us a good, reliable stream of calcium and magnesium. You know, we're getting sulfur. You know, we have a lot of different places we get sulfur into the system. Some of it comes in as, if you will, contaminants in some of our fertilizer sources. You know, we used to get a tremendous amount of sulfur coming in from the atmosphere as a result of, you know, fossil fuel combustion and volcanic activity and things like that. Secondary nutrients are important. You know, you need to be aware of those issues and think about it from a fertility standpoint. Usually you would see something on a soil fertility recommendation report if you have issues to be concerned about. Now, we do need to think and talk about the micronutrients a little bit more. Not necessarily because in our animal waste management systems that we see deficiencies, but because we may see toxicities. Now, historically, let's think kind of what's happened with regards to micronutrient fertilization. You know, over time, you know, we've got these crops that are growing with greater and greater yields. And as a result of these greater yields, they're pulling more and more nutrients out of the system. So what micronutrients might have been there are getting harvested out by the growing crop itself. Another factor is that you know, we have much more pure nutrient sources than we used to deal with. Think about the days of, you know, Great Granny growing tomato plants. You know, it was all manure-based type of systems. You know, that manure kind of is a hodgepodge of everything that the animals that generated had eaten. And so you have your nitrogen, you have your phosphorus, your potassium, some calcium, copper, zinc, sulfur, manganese, magnesium, cobalt. All that stuff is already in there, right? And so all those materials or all those nutrients kind of get applied just by default. Well, now in the world where we have, you know, nitrogen-only fertilizers or phosphorus-only fertilizers in the case of something like triple superphosphate, you know, we have these high analysis, relatively pure fertilizer sources that are not going to be providing us those contaminant nutrients that are actually needed at small levels, those micronutrients which are needed. Another issue is that, you know, we have gotten into this fertilization to where we are, you know, managing this Liebig's laws of minimums. So we're coming in here and we are correcting our problem for phosphorus, right? And so we're filling that board in this oat bucket approach, so that now nitrogen is a problem. What happens when we come in here and we correct our nitrogen problem? What is the next set of nutrients that we have to deal with? It's going to be those micronutrients. So as we solve our phosphorus problem, as we solve our potassium problem, our nitrogen problem, what is our next problem going to be? And so this has kind of come about, particularly since the end of World War II, as we've gone to these, you know, nitrogen phosphorus type of fertility management programs. Now we start thinking about the micronutrients. You know, we can think about things that are really needed in small amounts. You know, again, we're down here in these, you know, part per million, part per billion kind of concentrations down here. And the thing I want you to think about is you have deficiencies and you have Oops, let me erase that. Let's go this route. You have deficiencies, we'll do in yellow, and you have toxicities, we'll do in red. Alright? So a nutrient can be toxic, or a nutrient can be deficient. Wrong pen. So we have deficiencies and toxicities going on. And the other thing that you'll see on here is that, you know, the same concentration at which one nutrient goes from a deficiency to toxicity, such as iron, is a lot different at which another nutrient will go from that deficiency to toxicity kind of thing. So we have these varying amounts needed, and that amount needed varies with the particular nutrient itself. Alright? Keep in mind also that for any one of these, for example zinc, for any one of these, those particular nutrients can change with the pH. Hold on, let me turn off my phone here for a minute. Alright. So, alright. Nutrient concentrations, deficiencies, and toxicities. So we need to think about what do these plant nutrients do. Typically they are involved in photosynthesis, again back to this energy transport, fruit formation, water regulation, etc. So what happens if there's not enough available? Well, we get into these poor root growth situations, stunted plants, eventual plant death kind of scenario. So, you know, it's a toxicity issue or a deficiency issue kind of deal we have to deal with here. So let me explain to you this toxicity and deficiency a little bit more. So we think about plant growth increasing as we go in this direction. And what we see is that as we get and across this way we have increasing concentrations in the particular soil. So at some point we have this area where we have a deficiency amount, where we don't have enough nutrients in the soil to support that particular plant. So somewhere around here, alright? We don't have a high concentration of that plant nutrient, and so that plant is not going to grow very much. But as we add nutrients, we continue down in this direction. We add more nutrients, that plant starts growing, right? Keeps going, and then we reach its maximum amount of growth rate. This is that sufficiency range. This is what we're managing for in the North Carolina Department of Agriculture and Consumer Services Soil Test Index System. We're shooting for this sufficiency range. Now, we do achieve a point to where if we continue adding fertilizer from here to here, you know, we keep adding fertilizer, we're going to create so much, or have so much of that particular nutrient in the soil that we could end up getting into a toxicity range. And at that point, what happens, ooh, boy, that's a horrible looking one. Let's try that again. So we get into a toxicity range, and at that point, as you continue to add more fertilizers, the growth of the plant gets more and more stunted as it becomes more and more toxic to that system. Or as that nutrient becomes more and more toxic to that plant. So not all plants respond to all nutrients in the same way. And so you have some that are most likely to show deficiency. And this is, you know, obviously when we think about waste management plans, we're not thinking about cantaloupes or azaleas or lettuce, all right? This is just to give you an example that some plants show deficiencies to different nutrients. So, you know, here we have boron looking up this way. So alfalfa, corn, cotton may show boron deficiencies, but lettuce, oats, and pecans don't. Whereas zinc, you know, you may have zinc deficiency in pecans and corn, whereas you don't have a molybdenum deficiency in pecans and corn. All right. So not all crops are equally sensitive to deficiencies, and the same can be said about not all crops are equally sensitive to toxicities. So these are just examples of crops that are sensitive to toxicities, whether it be something like corn and Sudan grass, tall fescue. I'm just looking at the agronomic crops for us here. Soybeans or peanuts, all right? Thing I want to point out here, peanuts and soybeans, two that are either very sensitive or sensitive to certain toxicities. What happens when you get into a system to where you have achieved a level of concentrations in the soil such that it's higher than the peanuts can tolerate? So the concentration gets high, peanuts can no longer grow there. You've essentially limited your cropping options for years and years and years to come. Meaning, you achieve a zinc index that's 300 or 600. It may be 50 years before you can ever put peanuts back in that field. You continue to increase concentration, you may limit the fact that you can't grow soybeans. Continue to increase concentrations, you may limit the fact other crops kind of work their way out of the cropping system, to where basically you end up with very limited crops that you can deal with as you get into these really highly soil toxicity type of, or micronutrient toxicity type of scenarios. So let's change our gears for a minute and think about two of these nutrients in specific, two of these micronutrients. And that'd be copper and zinc. And the reason why we're focusing on these two is because these two have found their way into the animal waste regulations through Senate Bill 1217, where copper and zinc monitoring are required. So copper in the plant, you're talking about enzyme activation. It helps with this symbiotic nitrogen fixation thing that we've talked about today. Hey, viability of pollen, that's kind of important if you're relying on pollen to produce apples or peaches, right? It's required in relatively small concentrations, and crops that are sensitive to deficiencies or toxicities could be, deficiencies are small grains, and you can achieve or repair or overcome those deficiencies, if you will, with soil applications or foliar applications. We start thinking about where is copper tied up, and really we can think about being bound up in the soil organic matter, in those clay minerals, and it's typically most available at pHs lower than 5. So most available at pHs lower than 5. So that probably means as the soil gets more and more acidic, the availability of copper becomes greater and greater. So another way to think about that is if copper is highly available at low pHs, what if we increase the pH? Can we potentially deal with a phosphorus toxicity that way by manipulating the pH? And the answer to that is yes, we can. We'll talk more about that in a minute. All right. So toxicities, reduce plant growth, leaf chlorosis, reduce branching, thickening of the roots, those type of things. So toxicity is an issue with copper. Let's look at zinc. Again, it's one that's used in activation of enzymes. It's used in carbohydrate metabolism. An interesting thing about zinc is, and I don't know that we're really seeing this much in North Carolina yet, but as you get into really, really high concentrations of phosphorus, you can have what's called preferential uptake, in which the zinc, you can actually have a phosphorus-induced zinc deficiency, because the plant is luxury consuming phosphorus at such high levels it can't take up zinc. Now, soil pH increases, we start thinking about zinc availability decreasing. And again, this is that same kind of thing I was talking about with regards to copper. That, if copper is highly available at low pHs, if you increase the pH, then you can decrease that availability. So this is one of the things that we can do to manipulate the soil system to control some of these toxicity type of systems or situations, all right? Now, we start thinking about zinc toxicity, we start thinking about a pH dependency here. And it has a lot to do with, again, as the pH goes up, the availability of that particular nutrient goes down. So we can see something like a pH 6, a zinc index of 425 is where you might have problems on a peanut crop. Whereas if you're at pH 4.5, that same problem can happen at a zinc index of 212, all right? So we think of crops that are sensitive to zinc, we have peanuts. Intermediate sensitivity, we have cotton and soybeans. And as we continue to elevate zinc levels, then we have to worry about corn, Bermuda grass, and fescue. Now, in the regulations, one of the things that we talked about was that, you know, well, I think it's actually on the next slide. Oop. There we go, this slide. Well, let me come back to that in a second. We talk about zinc indexes and zinc toxicities, and, you know, zinc is one of those positively charged ions. It's a cation, right? And so it can get bound up on the cation exchange complex such that it's not as available to the plants. What you're looking at in this particular field here is, let me see if I can get the right color pen. Here we go. These relatively sandy portions of the field, like right there, where the zinc concentration is high, not because there's necessarily a difference in how much zinc has been applied, but the zinc concentrations are high because the cation exchange capacity is so low. So the availability of the zinc is much greater in these situations than in the clay areas, just, you know, right there, right there, right there. So let's look at the regulatory requirements. And we've talked about this in passing, you know, when we were talking about Senate Bill 1217 in a previous presentation. Let's kind of focus in on it now a little bit more with regards to zinc. And the way this works is basically when you hit a level of 300, you know, you need to be thinking about limiting your applications, looking for alternative sites, etc. And the reason being is because when you hit 300 and above, you've got to start worrying about peanuts. Sure, you may not be growing peanuts on that particular site now, but what happens if in 50 years the great cure for cancer comes up and it revolves around a peanut? Now, peanuts are all of a sudden extremely highly profitable then, correct? The problem is your zinc index is so high that you'll never get peanuts back into that particular field. All right, so you have to think down the road further than just next year when you start talking about managing these micronutrients. When you get to a level of 500, you know, and you're trying to grow peanuts, forget about it. You know, you don't want to put any more manure nutrients or any more zinc out there on those particular fields. When you get up to 2,000 and 3,000, you know, you need to start thinking about alternative sites. When you get to 3,000, you need to absolutely stop the application of zinc. Another point is here, maintaining pH. Again, that sliding scale of zinc's most available at lower pHs, it's less available at higher pHs. So if we can control our pH up to 6 somewhere, we can kind of maintain how much of that zinc is actually available in the soil, right? Let's go back to here. Remember our pH 6 versus pH 4 or 5. Looking at an index of 425 where you have problems versus 212. So if we can maintain our pH up in this range, you know, we can limit the potential damage to a particular crop. Copper, you know, we start thinking about warning versus stop. So a yellow light versus a red light. Caution when you get to 2,000. You know, you need to look for alternative sites and for alternative crops if possible. 3,000, whoa, stop it for all crops. And again, maintain your soil at that pH of 6 to control the availability of that particular copper nutrient element. Now, there are some things that can be done, and you know, one of the things that you can do is this deep tillage. And I guess this deep tillage kind of falls into that, approach of the solution to pollution is dilution. And then if you take a soil that you typically plow 8 inches and it has a zinc index of 400, and now you plow that soil not to 8 inches but to 16 inches, right? You could potentially cut that zinc index in half because you've diluted that material, across a greater depth. So you're back down to a 200. So you can see things like this where you get into these really deep tillage over here. You got these really deep tillage type of methods going on where we're trying to cut that zinc concentration or copper concentration simply by diluting it down lower into the profile. The other thing that you can do is if you could increase organic matter. That organic matter will bind up that copper and zinc and perhaps take it out of the soil solution to where it's not as toxic to the plant. Same concept with clay, although it's not very easy or not very economical. In fact, it's not economical at all to go out and add clay. But one thing that will happen is if you do some deep tillage, you will bring some of that subsoil clay up to the surface, which may have even greater benefit to that clay complexation of the zinc and copper other than just the solution to pollution is dilution. All right? The easiest thing to do other than organic matter is probably manipulate your pHs, and that's just a liming thing. If you've got high zinc and copper and your typical target pH is 6, maybe you need to up it to 6.2, up 6.3, something like that. It's going to cost a little bit more in lime, but controlling those nutrients versus taking that field out of production for a particular crop may be a cost that you're willing to pay. Now the question is, do you have a deficiency, a toxicity, or something else? And, I've got years and years and years of soil fertility background under my belt, but I still have difficulty in eyeballing which toxicity or which deficiency I'm actually looking at. Excuse me. And these 3 are examples right here. This soybean crop. This soybean crop over here looks like it might have some sort of deficiency or toxicity just looking at the leaves. Reality is, it's a bacterial infection. This looks over here in this azalea like it might be an iron deficiency, or a sulfur deficiency perhaps, this kind of chlorotic leaf thing. What do we have really going on here? We have a root rot problem. And this boxwood, we have a pesticide problem. So even the best of us struggle with what we have here. Deficiency, toxicity, all right, which nutrient is deficient, which nutrient is toxic, etc. And particularly in North Carolina, where we have the NCDA, the North Carolina Department of Agriculture and Consumer Services soil testing lab, it seems to me that when a service is free, it's not a bad idea to take a soil sample, not guess, and instead test. And so we're going to spend the last few minutes here talking about soil testing, particularly within regards to North Carolina. In North Carolina, we use that sufficiency soil testing approach. And what we're trying to do is provide or learn enough about that particular soil to understand something about what nutrients we need to apply economically that make an environmental that have minimal environmental impact on the plant nutrient status in the environment. All right, so we want to put out what the plant needs, but minimize what is left behind when the plant's gone. So that's the environmental aspect of it. We're trying to determine, how much lime do we need? Do we need lime? What nutrients do we need, etc. It's not a perfect science. It's a best guess approach, or soil testing. Now the question is, how do you take a soil sample? And for years, the North Carolina Cooperative Extension Service has been saying, wander around aimlessly, randomly poke holes in the field, deposit those samples, and submit those samples to the soil test. And what we've been saying is avoid areas that are very different and try and lump areas together that are the same. And so a very easy way of lumping areas together that are the same. Everybody's aware of Google Earth, Maps.Google, Yahoo Maps, Microsoft's Live Maps, whatever. Get on the internet, find the field you're worried about, and just look at it and take a color picture like this. And that's exactly what this is. This is off of Google Earth, I think. And you can quickly see how you can take a map like this and say, okay, there is one soil sampling area. There's another soil sampling area. You know, here's another soil sampling area. So you can divide these things up into the different soil sampling areas. And then you go out, and in this, you take your random samples and composite those into something that is a single sample, representing soil sample area A. Here's B. So here's going to be our random samples that represent B. So you get the picture. Now, when you're collecting these things, you know, you've got some obvious places you want to avoid. Let me explain to you what these are and why you want to avoid them. First of all, avoid wet spots. Wet spots are areas where there's not as much oxygen, and the lack of oxygen in the soil will completely change the chemistry of that particular soil. So don't sample wet areas and group them with dry areas. For obvious reasons, avoid manure and urine spots. If you're out sampling your lawn and you take a soil sample right where the dog left you a present, you know, the fertility underneath that particular sample, or underneath that particular present, if you will, is going to be a lot different than just about 2 feet away. So avoid those spots. Avoid places where you've burned wood in the past. Why is that? Well, when you burn wood, you generate ash, and that ash has a liming coefficient associated with it. It can affect soil pH, so you want to avoid old burn piles. Sample eroded areas completely separate than non-eroded areas, because the subsoil that is exposed is a lot different than the topsoil that's elsewhere. Old building sites and fence rows. This is the truth. Galvanized roofs are made of what? What kind of metal is in a galvanized roof? Well, galvanizing. Yeah. Well, what is that? Zinc. There's zinc in there, okay? So if you're sampling around an old farmhouse or an old farm, a fence row or something like that, you see a galvanized barbed wire fence that's now rusted, that means the galvanizing has washed off and it's underneath that fence. You can actually sample there and you will detect that zinc from either that roof or that barbed wire fence in that soil sample. So avoid those types of areas. Alright, where you know that the crops or fields have had different crops, avoid those particular areas. I remember working in a field a number of years ago, and we couldn't figure out why the left half of the field was so dramatically different than the right half of the field. And it just didn't make a lot of sense until we realized that, for 30 years, the left half of the field had been under one cropping system, and the right half of the field had been under a completely different one. And so as a result, these differences in the cropping system, we're seeing these, long-term lime applications are different in the left versus right. Long-term phosphorus applications different left versus right. So we have these dramatically different areas in the field that needed to be separated out. All right. Now, collect your samples in stainless steel or chrome-plated sampling tools, plastic buckets, avoiding contaminating the samples, right? And I've got this kind of little, what should be a little smiley face guy, but he's frowning with his police hat on saying, stop, warning, 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 right? What's the problem here? Well, you look at this picture and I can show you what the problem is. The problem is that guy right there. Those zinc, or that zinc bucket. Same with that zinc or that galvanized barbed wire fence. I shouldn't say zinc bucket. I should say galvanized bucket. That galvanized bucket's going to have the exact same problems for you as that galvanized fence and that tin roof kind of thing. You're going to get a lot of zinc. All right. So use a plastic bucket and make sure that that plastic bucket is not one that has been used for fertilizer application lately. If it's the one that your wife or your husband uses to go out and fertilize the tomato plants, wash it out really well, and then use it. Or get a completely different one. Use a completely different bucket. How deep do you sample? Well, that's a question of what are you growing. If you're looking at something that you're not plowing, so a fescue field, Bermuda grass field, no-till production, you probably sample to 4 inches. If it's something that you're plowing to a depth of 8 inches, then you sample to a depth of 8 inches. When you take a soil sample, and look at the, if you take a soil sample to be analyzed by the Department of Agriculture, essentially what they say is, plowed fields sample to a depth of 8 inches, unplowed fields to a depth of 4 inches. So that's the simplest way to think about it. Now, when you get into phosphorus loss assessment type of things, now there may be scenarios if you have high soil phosphorus in the surface that you're actually going to have to sample much deeper. And we're going to leave that issue for Dr. Osmond to address when we talk about the phosphorus loss assessment tool. So who can analyze it? Well, in the state of North Carolina, the best place to go is the North Carolina Department of Agriculture and Consumer Services Agronomic Division. Now, why would this be the best place? Well, they're free, first of all, and they do a top-notch job. Now, that's not to say that there aren't other places that can do it. There are private laboratories that can analyze your soil samples, but they're private laboratories. They're looking for dollars for doing your sample. So if speed is an issue, you may be willing to pay that private laboratory in order to get your soil sample analyzed much quicker. If cost is an issue, you may be able to wait that time frame that it takes to get your sample analyzed by the Department of Agriculture. I will say this, when you're sampling or submitting samples to the North Carolina Department of Agriculture for soil analysis, anything that you can do to time that sample such that it is between the months of April and August will do a great service for getting your samples back quicker. The closer you get to December with submitting a sample, the longer it's going to take for you to get your analysis back. And the reason being is because everybody is sitting there submitting their samples in the late part of fall. Alright, so closing slide. We've talked about this as soil testing is a free service by the Agronomic Division. I guess the final thoughts are where can you get instructions, and the best place for that is the County Cooperative Extension Service Centers. Fertilizer distributors will have boxes and sheets and things like that, as well as the North Carolina Department of Agriculture and Consumer Services regional agronomists. So that kind of concludes the soil chemistry and fertility review session. Next one up will be the soil online soil survey type of things, and we will have that presentation live next week and will be recorded for everyone else to view. Thank you for your attention today, and take care.